On April 6, 2026, at 6:44 in the evening Eastern Time, 4 human beings went somewhere they couldn't call home from. Not just out of range, not just delayed by the speed of light. The moon itself got in the way. The moon, 3,474 kilometers of solid rock. Craters stacked on craters for 4 billion years. Slid between the Orion spacecraft and every radio transmitter on Earth. Every frequency, every wavelength, every voice from Houston, every data stream from Mission Control, every emergency abort command. All of it blocked. For 40 minutes, Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen were unreachable. Not just the most isolated humans alive at that moment. The most isolated humans who had ever lived, at a distance no human being had ever maintained from Earth before. In a silence more complete than any capsule radio blackout. On the far side of a world that has been hiding something from us for the entire span of human history. What they saw in those 40 minutes, and in the hours before and after them, has been coming out slowly. In press conferences with careful language. In photographs, downlinked over days, because the bandwidth from deep space can only carry so much at a time. In descriptions from 4 astronauts who have trained themselves to be precise and calm, and who still kept reaching for words that weren't quite enough. Tonight, we're going to put it all together. Not the official summary, not the highlights reel. The full story. The geology, the physics, the silence, the things their predecessors buried for decades, and the things this crew has and hasn't said yet. By the time we're done, you'll understand what those 4 people actually experienced, and why Victor Glover, a Navy captain, a test pilot, a man who spent 168 days on the International Space Station without losing his composure, came back from the far side of the moon and told the world that what he had been looking at was probably beyond what human beings had evolved to see. Before we get started, if you love exploring the depths of space and the great unanswered questions of the cosmos as much as we do here, take a moment to like this video or subscribe to the channel. It helps more curious minds find their way here, and it keeps this journey going. Now, let's begin. Who these 4 people are and why it matters. Before we talk about what happened, we need to talk about who was there. Because the 4 people inside that capsule weren't just astronauts in a generic sense. Each one of them was carrying something into the dark that made this particular mission unlike anything the program had done before. Reed Wiseman is the commander. He's 51 years old. A Naval Academy graduate, a carrier-based fighter pilot, and the kind of person NASA selects as a mission commander after decades of watching how someone handles stress, ambiguity, and the specific quality of keeping your voice level when you have every reason to raise it. He'd been to space once before, a 6-month stint on the International Space Station in 2014. He knows what it feels like to be enclosed in metal above a planet. He knows the particular way time moves when you can't go outside. But there is something else Wiseman carried to the moon. Something that didn't show up in his mission biography or his NASA press kit. His wife Carol was diagnosed with cancer several years before the mission. She told him not to quit, not to move the family closer to relatives, not to let the diagnosis reshape the life they'd built together around his career and his belief in what he was doing. "This is where you work and you love your job," she said. "We should not give that up for this." She died in May 2020, at the age of 46. Wiseman raised their 2 daughters alone, kept training, and eventually strapped himself into a spacecraft headed for the moon. Before he boarded the rocket, He posted a photograph with his daughters Katie and Ellie and wrote that he was boarding the rocket, a very proud father. 6 years of raising 2 kids alone while preparing to go to the moon. And what he chose to say about it was that he was proud. Victor Glover is the pilot. He is the first black astronaut ever to fly beyond low Earth orbit. Not the first in a symbolic sense, not the first in a limited context. The literal first time in the history of the species that a black person traveled beyond the boundary where Earth's gravity gives way to the moon's. He was also the first black astronaut to spend an extended tour aboard the International Space Station, completing a 6-month mission in 2021. What Glover said after the mission about the far side of the moon, that it was beyond what human beings had evolved to see, was not poetic license. He is not someone who says things for effect. He is someone who says what he observed when he described the Terminator line along the moon's shadow boundary as full of magic, as islands of light above valleys that looked like black holes you could fall through to the center of the moon. He was giving you a geological field report in the only language that fit the observation. Christina Koch already held the record for the longest continuous spaceflight by a woman, 328 days on the International Space Station, from 2019 to 2020. She is a geophysicist, not just a pilot. She earned a degree in the field before joining NASA, which meant she was looking at the moon's surface below her with a different eye than most astronauts. When she described the color variations across the lunar surface, the subtle shades of brown and green on the near side, the blue tints in certain regions, the way craters looked like pinpricks in a lampshade glowing white against dull gray terrain. That was scientific observation, not tourist description. The human eye can distinguish color gradients that cameras flatten. What Koch was describing will matter to planetary geologists for years. Jeremy Hansen is a colonel in the Canadian Air Force, a fighter pilot, and an astronaut with the Canadian Space Agency. He is the first non-American human being to leave Earth's orbit since Sergei Krikalev on Soyuz TM-1/2 in 1991, and the first non-American astronaut to fly beyond low Earth orbit in the history of human spaceflight. He is also, based on everything he said during and after the mission, someone who understood exactly what this moment meant and refused to let it pass without saying so. At the moment when mission telemetry confirmed that Artemis II had broken the record for the farthest any human had traveled from Earth, 252,756 miles, beating Apollo 13's 35-year-old record by over 4,000 miles. Hansen spoke directly into the mission record. "We choose this moment," he said, "to challenge this generation and the next, to make sure this record is not long-lived." These are the 4 people. This is what they were carrying. Now let's talk about what they flew into. April 1st, 2026, Kennedy Space Center, Launch Complex 39. The Space Launch System rocket stands 322 feet tall. For reference, that's roughly as tall as a 30-story building, though shaped differently. A tapering column of white and orange hardware, topped by the Orion spacecraft and its launch abort tower. At the base, 4 RS. 2.5 engines originally developed for the space shuttle and refurbished for this role, and 2 solid rocket boosters that each generate more thrust than the Saturn V's outer strap-ons. At liftoff, the combined thrust is 8.8 million pounds. To put that in terms that means something, the Saturn V, the rocket that sent Apollo astronauts to the moon, generated 7.6 million pounds of thrust at liftoff. The SLS is more powerful than the rocket that sent humans to the moon in 1969. the most powerful operational rocket ever built, now in flight, now carrying people. The crew had been in their seats for hours. The countdown, the holds, the weather assessments, the final go/no-go polling of all flight controllers. All of it leading to the moment when the sound hit. Not the sound you hear on launch footage, which is the rocket's noise traveling through air to a microphone and then through speakers to your ears. The sound the crew felt, which is the vibration of 8.8 million pounds of controlled combustion moving through the vehicle structure and into the seats and into the bones of 4 people who had trained for years for this specific moment. Within about 2 minutes, the solid rocket boosters burned out and separated. The RS-25 engines continued. The vehicle pitched downrange over the Atlantic. Staging, then a single engine in the interim cryogenic propulsion stage. The upper stage, carrying Orion and the crew toward the required velocity for the translunar injection burn. About 90 minutes after launch, after one orbit of Earth confirming all systems were nominal, came the burn that made the mission irreversible. The translunar injection burn lasted less than 6 minutes. One engine firing continuously for less than 6 minutes. And at the end of it, Orion was no longer in Earth orbit. It was on a trajectory to the Moon, traveling at about 24,000 miles per hour, climbing steadily away from the planet. There is no pausing after that moment, no holding in orbit while you think it over. The spacecraft is going to the Moon. The question from that instant forward is only how the rest of it goes. The crew knew this. They had trained it, simulated it, understood it intellectually for years. And yet, every astronaut who has made this kind of burn and passed this kind of threshold describes something the simulations don't capture. The particular quality of a decision that can no longer be unmade. The door that is closed behind you, not violently, not with drama, but with the soft click of a latch that has no handle on the inside. The crew radioed down that everything looked good. The data confirmed it. Mission Control cheered, as Mission Control does. And then they settled in for the 3 days it would take to reach the Moon. The Orion spacecraft's crew module is roughly the shape of a large ice cream cone, about 16.5 feet in diameter at the base. The pressurized volume inside is about 316 cubic feet, enough for 4 people and their equipment, though not spacious by any standard. There are 4 seats for launch and landing, and a small amount of space to float around in once you've unbuckled. There are windows, 4 of them, facing different directions. The first thing that changes, leaving Earth orbit, is what the windows show. In low Earth orbit, where the International Space Station lives, where every other crewed mission in the decades since Apollo had stayed, the view out the window is dominated by Earth. The planet fills the lower half of your visual field. It's enormous. Its colors are vivid. Its cloud systems move visibly. Weather patterns the size of continents scroll past below you. It's impossible to look at Earth from 250 miles up and not feel grounded by it, anchored to it. It's right there. On a translunar trajectory, the first thing that happens is Earth gets smaller. Not gradually enough that you don't notice. Fast enough that if you look away and look back an hour later, you can measure the difference. By day 2, Earth is a sphere in the window, no longer filling the frame, no longer a surface you're skimming, an object distant enough to see its shape completely, close enough that you can still make out the blue of ocean and the white of cloud cover, and, at certain angles, the faint rust of a continent. By the time Orion was approaching the Moon, 3 days after launch, Earth had shrunk to roughly the apparent size of a golf ball held at arm's length. still visibly blue. Still obviously the place everything had come from, but small enough to cover with your thumb. The stars, meanwhile, don't look the way they do in the popular imagination of space. They don't blaze. They don't shimmer dramatically. Their points hard and steady, in a blackness that is different from any blackness you've experienced inside an atmosphere. Terrestrial darkness is never absolute. There's always scatter, reflection, the faint glow of a horizon. This darkness has no scatter, no reflection. The stars are points and the space between them is genuine void. The effect is that the sky looks less dramatic than expected, not more real, more final. The crew was busy. Every major system on a spacecraft that has never carried people before needs to be tested in the real environment. Life support verification, navigation system checks, manual piloting practice, communication system tests, medical monitoring, sleep cycles, meals. The specific routines that keep 4 people functional when the functional is the only thing keeping the mission alive. But there were windows, and there was time. Glover, whose photography from previous space missions had been extraordinary, was documenting everything. Koch, looking at the lunar surface they were approaching with a geophysicist's trained eye, was making notes. Hansen, the first non-American to reach this distance, was thinking about what he was going to say when the moment came. And Wiseman, commanding all of it, was doing what commanders do, tracking the state of every system and every person simultaneously, looking for the thing that isn't quite right before it becomes the thing that is wrong. There is something worth sitting with about the 3 days themselves. Not the launch, not the moon arrival. The transit. The middle part that doesn't get footage because there isn't much to film. Just 4 people and a spacecraft. And the growing distance. The Orion crew module was never designed to be spacious. It is roughly 316 cubic feet of pressurized volume. For context, that's about the size of a large walk-in closet. Except it is also the kitchen, and the bedroom, and the bathroom, and the control room, and the laboratory, and the office, and the only place you can be. You can float around in it. You can push off one wall and drift to the other. Microgravity makes the ceiling a floor, and the floor a ceiling, and eliminates the distinction between lying down and standing up, which frees some psychological space even when the physical space remains fixed. But it is a small world. Inside that small world, for 3 days the crew was doing the technical work of the mission, verifying systems, conducting science experiments in the onboard biology payload, communicating with mission control in the regular scheduled voice, passes that punctuated the silence between. The Avatar experiment, one of the biological science payloads the crew was monitoring, contained bone marrow cells derived from the crew's own blood samples. The experiment was designed to study how bone marrow cells respond to the deep space radiation environment. Data that pharmaceutical researchers will use to understand whether it's possible to develop radiation protective treatments for astronauts on future long-duration missions. The crew checked its status. The data was accumulating. But between the procedure calls and the systems checks and the scheduled communication windows, there were hours. Time at the windows. What you notice, leaving Earth orbit for the first time, is that the stars don't wheel the way they do from the ISS. In low Earth orbit, you complete a full circuit of the planet every 90 minutes. The visual field rotates. The terminator between Earth's day and night side sweeps past beneath you once every hour and a half. Day and night cycle in the most literal sense. not 24-hour Earth days, but a 90-minute cycle of full illumination and orbital darkness. 16 sunrises per Earth day. On a trans-lunar trajectory, the spacecraft isn't orbiting anything. It's traveling in a straightish line, curved by gravity, but not completing circuits. The stars hold their positions relative to the spacecraft. If you're pointed in a particular direction, you see the same stars when you wake up as when you went to sleep. The moon grows in the forward view. Earth shrinks in the rear view. Everything else stays fixed. There is a quality to this that is different from orbit. Orbit, even in the vacuum of space, has a rhythm. The rhythm of the planet below you, cycling from ocean to continent to night and back. It gives you something to track, a reference point, a sense of the passage of time grounded in the turning of a world. Translunar cruise doesn't have that. Time passes by the clock and by the schedule, not by anything you can see out the window. The universe outside is exactly as it was 8 hours ago. The moon is slightly larger. Earth is slightly smaller. Everything else is unchanged. Several astronauts who've described deep space transit, and the sample is small, only the Apollo crews have experienced it, describe a strange quality to the perception of time. Not disorientation, not distress, but something closer to what people describe when they're in a very quiet, very empty natural environment. The absence of the usual cues that mark time's passage. A stillness that the brain doesn't quite know what to do with. The Apollo 11 crew logged 76 hours of translunar coast between leaving Earth orbit and entering lunar orbit. Collins wrote about it in his memoir with a characteristic precision. Not frightening, but genuinely strange. The spacecraft feels enormous compared to the scale of space around it, yet completely insignificant within it. Both things true simultaneously. The Artemis II crew had about the same duration of translunar coast. 4 people. A spacecraft the size of a large living room. The growing certainty of the moon ahead. The shrinking certainty of Earth behind. The radiation environment they were flying through deserves its own moment of attention, because it is one of the things that press conferences tend to mention briefly and move past. Earth has a magnetosphere, a vast magnetic field generated by the planet's liquid iron core extending tens of thousands of miles into space in every direction. The magnetosphere deflects most of the charged particles streaming out from the sun, and it deflects most of the galactic cosmic rays. The incredibly high-energy particles produced by supernovae and other catastrophic stellar events that arrive at our solar system from all directions. Inside the magnetosphere, human beings are substantially shielded from both. Beyond the magnetosphere, they are not. The International Space Station orbits within the outer reaches of the magnetosphere. The crew on the ISS receives elevated radiation compared to humans on the surface, but they're still partially shielded. Artemis II was not. From the moment Orion passed the magnetopause, the outer boundary of Earth's magnetic field, all 4 crew members were exposed to the full interplanetary radiation environment. Solar energetic particles from the sun. Galactic cosmic rays moving at fractions of the speed of light, capable of penetrating not just the walls of the spacecraft, but the bodies inside it, passing through flesh and bone and leaving ionization trails as they go. Those trails cause DNA strand breaks. They cause changes in cells that can, over long enough exposure, become cancer. This mission was taking place during solar maximum, the peak of the sun's 11-year activity cycle, when solar activity is highest, when the frequency of solar particle events is at its greatest. A major solar particle event can push radiation doses to near lethal levels within hours. The Orion capsule has more radiation shielding than any Apollo capsule did. The design specifically incorporated lessons learned from the Apollo era about the biological cost of deep space exposure. But no amount of shielding stops galactic cosmic rays. They have too much energy. They punch through everything. Every Apollo astronaut reported seeing light flashes with their eyes closed during lunar missions. Not imagined, not psychological, but real. High-energy particles passing directly through their retinas and triggering the visual cortex. The particles were real. The light was real. It was just invisible to everyone else in the capsule. The Artemis II crew experienced the same phenomenon. By the time they returned to Earth after 10 days in deep space, each of them had absorbed a radiation dose that will require lifelong medical monitoring. Not a dose that will kill them. Not a dose that will immediately affect their health, but a dose that accumulated inside their cells and will be tracked for the rest of their lives. This is the reality of leaving Earth's magnetic field that gets mentioned in bullet points and then passed over. It is the thing that stands between humans and Mars, more fundamentally than any engineering problem. You can build a better rocket. You can build better life support. You cannot simply build a shield that stops galactic cosmic rays without making the spacecraft so heavy it can't fly. The crew knew this going in. They accepted it. They flew anyway. There is a detail here that doesn't get mentioned in the mission summaries. The Avatar payload, one of the biological science experiments the crew was monitoring, contained bone marrow cells derived from the crew's own blood samples. Not generic donor cells, theirs. The experiment was designed to study how human bone marrow responds to the specific deep space radiation environment, using samples genetically identical to the people in the spacecraft. The data those cells accumulate during 10 days outside Earth's magnetic field will be more valuable to pharmaceutical researchers than any general experiment could be, because the radiation exposure the cells experience is precisely what the crew experienced. Same trajectory, same timeline, same solar conditions. That research is ongoing. The cells came back. The data is being analyzed. In some form or another, the crew's own biology is still at work, figuring out what 10 days in deep space did to them, and what that means for everyone who goes after. Alexandra Stankovic, founding director of the Center for Space Medicine Research at Massachusetts General Hospital, has described deep space radiation as the #1 limitation on how far humans can explore. Not propulsion, not life support, not psychological endurance, not the enormous engineering challenge of keeping people alive in a hostile vacuum. Radiation, the thing you cannot engineer your way around at any reasonable scale. The thing that accumulates invisibly in every cell, in every body, every hour spent outside Earth's field. The thing that doesn't care about your trajectory or your mission objectives or anything else. The crew spent 10 days outside that field. 3 days out from Earth, the moon had grown from a bright point to a disk, to a world with visible geography. As Orion curved onto its approach trajectory, the crew had their first sustained views of the lunar surface at close range. Not through telescopes, not in processed satellite images, but through the windows of a spacecraft flying about 4,600 miles above the surface. And what they were flying toward was one of the most geologically strange objects in the solar system. We need to spend time here, because the far side of the moon is not simply the back of something familiar. It is a fundamentally different world from the side we see every night. Understanding how different it is and why changes everything about what the crew experienced when they crossed into it. The moon's near side, the face that has always pointed toward Earth, is covered in what planetary scientists call maria, vast dark plains of ancient solidified lava. These are the features that give the moon its face, the ones humans have looked at and imagined into shapes for thousands of years. The man in the moon, the rabbit in the moon in East Asian tradition, the face that children trace with their fingers, all of it is the pattern made by these dark volcanic plains. They cover roughly 31% of the near-side surface. The far side has almost none of this. Less than 1% of the far side is covered in volcanic plains. Instead, the far side is a wall of craters, ancient craters containing younger craters, containing still younger craters, stacked and overlapping in a record of 4.5 billion years of bombardment, from which the near side was largely protected by the lava flows that buried those older scars. The far side looks like something took a hammer to it for the entire history of the solar system and never stopped. The crust on the far side is roughly 50 kilometers thicker than the near side's crust, 50 kilometers of extra rock. Nobody fully agrees on why. The leading hypothesis involves a massive ancient impact near the moon's south pole, so violent that it sent a shockwave of heat and material through the entire lunar interior, pushing radioactive elements and heat-producing minerals toward the near side. That heat differential drove the volcanic eruptions that produced the maria on the near side. The far side, cooler and geologically quieter, never had the volcanic flooding that buried its ancient craters. That impact left something behind that the Artemis II crew flew over at closest approach. The South Pole Aitken Basin, the largest preserved impact crater in the entire solar system. It stretches approximately 2,500 kilometers across and plunges up to 13 kilometers deep. To put that in scale, placed over the continental United States, it would cover everything from the Texas coast to the Virginia coastline. Its walls are mountains. Its floor, at the deepest points, is 13 kilometers below the surrounding terrain, deeper than any trench in any ocean on Earth. And under that floor, something enormous is buried. In 2019, a team of researchers led by planetary geophysicist Peter James at Baylor University combined gravitational data from NASA's Grail spacecraft with topographic measurements from the Lunar Reconnaissance Orbiter. What the data revealed was a mass anomaly at depth, a concentration of dense material sitting at least 300 kilometers below the basin's surface. The anomalous mass is estimated at a minimum of 2.18 quintillion kilograms. James described it as roughly equivalent to burying a pile of metal 5 times larger than the Big Island of Hawaii underground. It is heavy enough to measurably distort the local gravity field, heavy enough to pull the basin floor downward by more than half a mile. And it is almost certainly the metallic core of the asteroid that created the basin in the first place, a projectile from the early solar system. Its iron-nickel core still lodged in the moon's mantle after 4 billion years, like a bullet that never came out. The Artemis II crew became the first humans to fly over the eastern edge of this basin with their own eyes. The Apollo astronauts never saw it. Their trajectories didn't carry them over the right regions of the far side, and the illumination geometry during their missions was wrong for the features they would have been looking at. Artemis II's trajectory was chosen partly to expose a wider swath of the far side at the right solar angle for observation. They saw what no human had ever seen directly. But the basin and its buried mass aren't the only strange things. In 2023, researchers analyzing thermal data from orbiting spacecraft detected something unexpected on the far side surface. A thermal anomaly approximately 50 kilometers wide, registering roughly 10 degrees Celsius warmer than everything around it. The heat source buried below the surface appears to be a massive intrusion of granite. Granite should not be on the Moon. On Earth, granite forms through processes that require both water and plate tectonics. A wet, chemically active geological environment in which silica-rich magma is processed over millions of years in ways that produce the mineral composition granite requires. The Moon has no plate tectonics. The Moon, as far as anyone knew before this discovery, had no granite. The researchers concluded that the thermal anomaly is almost certainly the remnant of a large ancient volcano that went dormant roughly 3.5 billion years ago. Its solidified magma body still radiating faint heat into the present day, still warm enough to show up in thermal surveys as an anomaly. Lead scientist Matt Siegler described the finding as something that looks far more like what we see on Earth than anyone had thought possible on the Moon. A feature that, by standard models of lunar geology, shouldn't be there. Still faintly warm, still marking its location with residual heat that has persisted for 3.5 billion years. What else is warm under there? That question, asked by Siegler in the published research, not rhetorically but as a literal scientific opening, is one of the things hanging over every observation the Artemis II crew made. Before we move on to the magnetic anomalies, there's one more thing the Moon is hiding beneath its surface, that Artemis II's observations were partly designed to help understand. The lava tubes. When ancient lava flowed across the Moon's near side billions of years ago and created the Maria, it didn't always flow as open streams. Sometimes it flowed inside channels that developed a solidified roof, a crust of rock forming over the flowing magma, creating a tunnel. When the lava inside eventually drained, what was left was a hollow tube, a tunnel of solid rock, empty inside, potentially kilometers long, potentially large enough to shelter something the size of a city block. These structures exist on Earth. Hawaii has extensive lava tube systems. Lanzarote in the Canary Islands has a 1.5-kilometer lava tube that has been walked through by tourists for decades. We know they form, we know they can be large, and the physics of lava tube formation suggests that on the Moon, where the lower gravity and different flow dynamics of ancient lava flows would have produced different thermal gradients, the tubes may be enormous compared to anything on Earth. Radar data from orbiting spacecraft has identified what appear to be pit entrances to potential lava tube systems in several lunar locations. These pits are holes in the surface, circular collapse features that expose the interiors of underlying voids. The Marius Hills region on the near side has one of the clearest candidates. A pit, roughly 65 meters across, and an estimated 80 to 100 meters deep, dropping into what the radar data suggests is a larger horizontal void. If these are confirmed lava tubes, their significance for future lunar habitation is enormous. On the Moon's surface, the temperature swings between approximately 127 degrees Celsius during the lunar day and minus 173 degrees Celsius during the lunar night. The surface has no atmospheric pressure, no radiation shielding beyond whatever the immediate terrain provides, and is continuously bombarded by micrometeorites and cosmic rays. Building a permanent habitat on the surface means engineering a structure that can withstand all of this, continuously, for years. Inside a lava tube, none of this applies. The temperature is stable, Deep inside the rock, insulated from the surface's thermal extremes, the temperature would be roughly constant at around -20 degrees Celsius. Cold, but manageable and constant. The meters of rock overhead provide radiation shielding comparable to being underground on Earth. The micrometeorite bombardment is irrelevant, because you're under a roof. The pressure differential is whatever the habitat is designed to maintain, not something the environment is fighting against constantly. A lava tube is, in a very real sense, the moon offering to shelter you. Ancient geology doing the hard work that would otherwise require engineering. Future Artemis missions will potentially investigate these tube entrances directly. Some may be accessible by robotic precursor missions. Some may be explored by the first astronauts to land on the moon in the Artemis II mission. What might be inside them? Undisturbed regolith that hasn't seen solar wind in billions of years. Preserved volatile deposits, a temperature environment radically different from anything on the surface, is genuinely unknown. No instrument has ever been lowered into a lunar lava tube. Whatever is inside has been sealed since the lava that created them solidified. The Artemis II crew was not in a position to directly observe tube entrances from their orbital altitude. They were flying too high, moving too fast. But their observations of surface geology, of shadow behavior along the terminator, of the way the light caught terrain features that processed satellite imagery had flattened into indistinctness, will feed into the planning for the missions that will investigate these features up close. The moon is not a known object. We landed on it 6 times in the 1960s and 1970s and collected rocks from a handful of sites on the near side, all within a relatively small area of the total lunar surface. We built models from that data and from decades of orbital observation and told ourselves we understood it. The Artemis II crew's observations of the far side are a correction to that confidence. Everything from the granite that shouldn't be there, to the metallic mass buried in the Orientale Basin, to the warm thermal anomaly, to the sealed lava tubes whose interiors nobody has ever seen. The moon has been keeping secrets that we haven't had the tools or the presence to find until now. And then there are the magnetic ghost swirls. The moon has no global magnetic field. It hasn't had one for billions of years. Its core cooled and solidified long ago, ending the dynamo process that generates a planetary magnetic field. But scattered across the lunar surface, particularly on the far side, are patches of magnetized rock, localized regions where the ancient field left an imprint in the crust before dying, like a compass needle frozen in place at the moment of geological death. Some of these magnetic anomalies are associated with features called lunar swirls, bright, curving optical markings on the surface that have no topographic relief, no physical height or depth. They look like someone painted white brushstrokes across the grey regolith. They are flat optical patterns that perfectly align with the local magnetic anomalies beneath them. The leading hypothesis is that the localized magnetic fields of these anomalies deflect the solar wind, the continuous stream of charged particles from the sun, creating small protected regions where the surface material isn't weathered and darkened by solar bombardment the way unprotected regolith is. The unprotected rock darkens over thousands of years. The protected regions stay bright. The pattern of the magnetic deflection is the pattern of the bright swirl. One of these swirls, called Rhina Gamma, sits on the near side's western hemisphere and was one of the observation targets the crew was photographing as they approached the far side. It's been observed from Earth for centuries without explanation. Only in recent decades did the connection to magnetic anomalies become understood. And even now, the explanation isn't completely settled. The Artemis II crew photographed it at resolution no orbiting spacecraft had matched, and those photographs are still being analyzed. As Orion curved around the Moon's western limb and the far side came into view, the crew's communications with Earth began to degrade. The Moon's curvature was blocking more and more of the signal path. Glover was still radioing down observations, descriptions of the terminator, the boundary between lunar day and night, which at their angle was a dramatic division between full illumination and absolute shadow. Along the terminator, what happens to craters is unlike anything visible from Earth. Sunlight striking at an extreme grazing angle, nearly parallel to the surface, creates shadows of extraordinary depth. A crater rim that might be a few hundred meters high casts a shadow that plunges its interior into total darkness, not the softened shadow of a room with ambient light, but absolute black. The kind of black that has no detail, no gradients, no information. Just the termination of light, and at the same time, the rim itself, catching the near horizontal light, glows brighter than it would under overhead illumination, bright enough to seem almost self-luminous against the surrounding darkness. Glover described what he was seeing as valleys that looked like black holes you could fall straight through to the center of the Moon. Islands of light, surrounded by darkness so total it seemed to have depth. He said the Terminator was full of magic, and he said it not as a poetic reach, but as the most accurate description he could generate in the time available. At 6:44 Eastern Time, the signal cut. The Moon's bulk had completely blocked the line of sight between Orion and every receiving station on Earth. The final voice contact before blackout was cut off mid-transmission. Mission Control acknowledged the expected loss of signal. The large screens at Houston showing Orion's telemetry went to static, then to projections. The tracking screens showing where Orion was calculated to be based on physics, not on live data, because live data was no longer flowing. In the capsule, the crew was in the far side. Let's be precise about what those 40 minutes were. The crew was not simply out of radio range in the way a hiker goes out of cell phone coverage in a mountain valley. The Moon itself was physically between them and Earth. 3,474 kilometers of solid rock, a planetary body, the fifth largest moon in the solar system, the same object humans have used as a calendar and a god and a navigation aid and a mystery for all of recorded history, was sitting between Orion and every other human being. There was no angle around it, no relay satellite in position to bridge the gap. There would not be one until future missions established the communication relay infrastructure that missions like this, one, are partly designed to justify. For these 40 minutes, there was only the Moon and the capsule on one side, and everything else on the other. The crew had trained for this. The blackout was expected, planned for, baked into every simulation. They had procedures that accounted for it. They had protocols for what to do if a system failed during the blackout, when there was no possibility of consulting mission control. The decisions in those 40 minutes were theirs alone. But training for something and experiencing it are different things. Every astronaut who has described communications blackouts, whether from orbital mechanics, re-entry plasma, or lunar occultation, makes this distinction. You can simulate the silence. You cannot simulate what that silence means when it's real. Consider the specific character of this silence. Inside the capsule, the crew could still communicate with each other. The intercom worked. The life support systems were running normally, the computers were processing navigation data, and system status and all the routine information that keeps a spacecraft functioning. It was not quiet inside Orion in any physical sense. The hum of fans, the whisper of the environmental control system, the sounds that a working spacecraft always makes were all present. But the absence of Earth was complete. There was no ambient carrier signal from the deep space network. The small, constant presence of that signal, the knowledge that it was there, that it could be used, that Houston could hear you if you needed them, was gone. Not degraded, not weak. Gone. The radio receivers were working perfectly and receiving nothing from that direction, because there was nothing to receive. For the Apollo crews who experienced the same blackout, the descriptions are remarkably consistent across missions. Not panic, not crisis, but a quality of isolation that doesn't have a clean, earthly equivalent. You can go to the most remote place on Earth, an Antarctic plateau, the middle of the Pacific Ocean, and you are still on the planet. You are still within the electromagnetic reach of civilization. Satellites pass overhead. Radio waves from human transmitters reach you. The background presence of Earth is there at some level, even in the most remote terrestrial places. On the far side of the Moon, it isn't. What it means operationally. If a solar particle event had erupted from the Sun during those 40 minutes, Mission Control would not have known until the signal returned. They would have detected the event. Space weather monitoring satellites would have flagged a particle flux increase immediately, but they would have had no way to warn the crew. No way to receive confirmation that the crew was taking cover. No way to know whether 4 people were getting a dangerous dose. Their next information about the crew's status would be whatever came through when the blackout ended. What it means practically. If the Orion spacecraft had experienced a catastrophic failure in those 40 minutes, a breach, a critical system failure, anything requiring emergency intervention, Mission Control would have had 40 minutes of not knowing. Not the specific anguish of knowing something is wrong and being unable to help. The absolute blankness of no information at all. The large screens in Houston showing Orion's telemetry go to projections, calculations of where the spacecraft should be based on the known orbital mechanics, not live data. The displays are showing you where physics says they are, not where they actually are. Flight Director Jeff Radigan described his team's posture during the blackout with the kind of carefully controlled understatement that flight directors specialize in. We'll just be thinking through things to keep ourselves calm as we wait for reacquisition of signal, he said beforehand. Think about what that means. A room full of the most capable aerospace professionals in the world, people who have spent years training for exactly this mission, staring at screens that show projections, listening to speakers that broadcast silence, knowing that 4 colleagues are on the far side of a planetary body and that the next voice they hear will either confirm that everything is fine or confirm that it isn't, with no information in between, for 40 minutes. The crew was not sitting in crisis mode during those 40 minutes. They were working. They were doing exactly what they had been trained to do, conducting far-side observations, photographing the targets on the science list, managing the spacecraft systems, talking to each other about what they were seeing. Wiseman was tracking the spacecraft status the way commanders always are. Coach was photographing the geological features below them with the methodical attention she'd been practicing for years. Hansen was noting observations, making sure the record was complete. Glover was at the controls, monitoring the navigation system, managing the systems that kept all 4 of them breathing in a sealed capsule on the far side of the Moon. They were professional. They were focused. And they were seeing things that no human eyes had ever seen. from a position no human had ever occupied, in a silence no human had ever experienced, from quite this far away. And somewhere in all of that, the far side was passing beneath them. At their closest approach, approximately 4,600 miles above the surface, the moon was not an abstraction. It was a terrain, a specific, particular terrain that Glover later described as not what you expect when you expect a grey ball. The ancient surface had color, subtle but real. Brown tints, hints of something that wasn't quite grey. The regolith, the fine-grained surface material produced by billions of years of impact gardening, has been chemically altered by solar wind bombardment in ways that produce variations in reflectance that human eyes can detect, but that cameras tend to average out. Koch, with her geophysicist's eye, was documenting these variations systematically. Below them was the Orientale Basin, a 600-kilometer-wide impact scar that straddles the boundary between near and far sides, nearly 3.8 billion years old. From the orbital angle and illumination the crew had been given by the trajectory designers, it was visible in a way that no orbiting camera had ever quite captured it. A bullseye in ancient rock, surrounded by concentric rings of ejected material frozen in place the moment of impact. One of the most visually dramatic geological features on any body in the solar system, seen by human eyes for the first time. Beyond it, deeper into the far side, the craters became denser. Not just physically denser, more ancient. The far side surface records impacts that occurred before the lava flooding on the near side erased those same records there. Looking at the far side from close range is looking at the moon as it was in its earliest geological epoch, before anything had been covered up. Koch noted the crater Vavilov, perched on the rim of the larger Hertzsprung Basin, deep in the far side. Hansen noted impact features, whose shadows were doing things that the simulation imagery had not prepared him for. The combination of the low solar angle, the extreme age of the terrain, and the complete absence of any atmospheric softening. No air on the moon, no scattered light, no diffuse glow from a sky that doesn't exist, meant that the shadows were more absolute, and the illuminated surfaces more starkly bright than anything they had trained to see. Then the sun went out. As Orion curved around the far side at its closest approach, the sun dipped behind the lunar disk. This was a total solar eclipse, but not the kind visible from Earth, where the moon barely covers the sun and totality lasts at most a few minutes and only along a narrow strip of the planet's surface. From Orion's position, totality lasted approximately 54 minutes. From Earth, a solar eclipse works because the moon and the sun happen to be almost exactly the same apparent size. The moon is much smaller than the sun, but much closer, and the coincidence of their apparent sizes produces the dramatic moment when the moon's disk exactly covers the solar disk, and the corona becomes visible. From a spacecraft at low lunar altitude, the geometry is different. The moon is close, enormous in the sky. The sun is blocked thoroughly, completely, with margin to spare. For 54 minutes, the crew was in shadow, not the shadow of a cloud or a building or the Earth's terminator. The shadow of the moon, at a distance where the moon fills a vast portion of the sky, with the sun hiding behind it. And around the moon's entire rim, the corona. The solar corona is the sun's outer atmosphere, a region of extremely thin, extremely hot plasma, extending millions of kilometers from the solar surface. Under normal circumstances, the corona is invisible because the photosphere, the bright surface of the sun, outshines it completely. It takes a total solar eclipse, with the photosphere blocked by the lunar disk, for the corona to become visible to the naked eye. From Orion's position, with the moon's disk blocking the sun, the corona spread outward from every point of the lunar limb simultaneously, not just from the edges, but from the entire rim. Glover described it as bright enough to ring the entire moon, a complete halo of solar atmosphere, glowing white and structured, reaching outward into the void in plumes that traced the sun's magnetic field lines. No human being had ever seen this. Not from this geometry, not from this angle, not with this duration of totality. Hansen described the corona illuminating the lunar limb in a way that highlighted the topography along the moon's edge. Ridges and peaks and crater rims silhouetted against the white fire of the sun's atmosphere. Mountains on the moon, visible not because the sun was illuminating them, but because the sun's corona behind them was illuminating their negative space. Wiseman and Hansen both noticed something else during the eclipse. Something smaller. On the darkened surface below them, brief flashes of light. Millisecond duration pulses of white-blue brightness scattered across the far side's unlit regolith. The crew counted at least 6 of them. Here is what those flashes were. The moon has no atmosphere, no air, no magnetic field of any consequence, nothing between its surface and the full violence of the interplanetary environment. Every piece of material traveling through the solar system, every dust grain, every centimeter-sized rock fragment, every micrometeorite, strikes the lunar surface with its full orbital velocity intact. Nothing slows it down before impact. A micrometeorite impacting at 30 kilometers per second, a typical velocity for solar system debris, doesn't leave a gentle dent. The kinetic energy converts essentially instantaneously to heat. The impactor and the surface material beneath it vaporize. The vaporized material expands outward in a flash that for a fraction of a second is genuinely bright, hot enough to emit light across a broad spectrum, including the visible range. On Earth, these events are invisible because they happen in the upper atmosphere, and the object burns up before hitting the ground, or because any surviving impactor lands on a surface where the flash is absorbed by soil and vegetation and scattered by air. On the moon, in a vacuum, on a dark surface, during a 54-minute eclipse that had adapted the crew's eyes to near absolute darkness, those flashes were visible. The crew described them as Wiseman would later, approximately as long as a camera shutter opening and closing. Pinpricks of light in Jeremy Hansen's words. White to bluish white. At least 6 confirmed observations. When the descriptions came through to Houston after the blackout ended, because the crew described what they had seen as soon as communication was re-established, the reaction from the lunar science team was audible, screams of delight, according to lunar science lead Kelsey Young. Nobody had expected the crew to observe any impact flashes. The probability had been considered low, given the crew's viewing geometry and the short duration of the eclipse window. They saw 6. This matters beyond the drama of the moment. Every future human presence on the moon will have to contend with micrometeorite bombardment. An impactor the size of a grape, moving at 30 kilometers per second, carries more kinetic energy than a grenade. Habitat walls, spacesuit materials, solar panels, any exposed surface of any structure built on the moon is vulnerable to this constant, statistically predictable bombardment. The flux rate, how many impacts per square meter per year, is one of the key engineering inputs for designing lunar infrastructure. The crew of Artemis II, by happening to be in the right position during a 54-minute eclipse window, directly observed a phenomenon that ground-based observers can only study indirectly with sensitive telescopes pointed at the dark portion of the Moon's disk. 6 direct human observations of lunar micrometeorite impacts, with position and apparent intensity reported in real time, cross-referenced against orbital satellite data. That's a small but real contribution to the dataset that will eventually tell engineers whether it's safe to build a lunar base, and where, and with what materials. 6 flashes, each lasting a millisecond, seen by human eyes for the first time in history. Before the crew went into the far side blackout, there was a moment that Koch described with a clarity that cut through every technical detail of the mission. Earth, set behind the lunar horizon. As Orion curved around the Moon's limb, Earth, already shrunken to approximately the size of a golf ball at arm's length, already recognizable as a pale blue sphere rather than a surface, slid toward the lunar horizon. The horizon of the Moon, at their altitude, was a stark arc of grey rock against the black of space, and Earth, the pale blue crescent of it visible, because only the part lit by the sun was visible from this geometry, descended toward that horizon and disappeared. Not the way the sun sets on Earth, slowly, reddening through atmosphere, softening as it goes. The Moon has no atmosphere. Earth went from visible to invisible in the time it took the orbital geometry to move it below the limb. No gradual dimming, no atmospheric distortion. It was there, and then it wasn't. This image, officially named EarthSat, is a companion to one of the most famous photographs in human history. In December 1968, Apollo 8 astronaut Bill Anders looked out a window above the lunar horizon and saw Earth rising above the grey desolation below. Earthrise. The photograph he took that day is credited with helping launch the modern environmental movement. The first time most humans viscerally understood that Earth was a specific, bounded, finite object floating in space. Artemis II's EarthSat is the inverse. Earth not rising above the Moon, but setting behind it. Not arriving into view, but leaving. Not the beginning of a perspective, but its end. Earth disappearing behind the world that has no air, no life, nothing between you and everything that wants to kill you. Koch described watching EarthSat with a precision that made it impossible to miss what she was actually saying. She said that when you have that perspective and compare it to home, it reminds you how much we have in common, that everything we need, Earth provides, and that you can't truly understand that until you've had the perspective of the other. Everything we need, Earth provides. Said by a woman 252,000 miles from Earth, watching it disappear behind a world where nothing has ever lived, where the temperature swings 500 degrees between sunlight and shadow, where every square meter of surface is being bombarded by particles from across the solar system, where nothing in the environment has ever been shaped by anything other than the physics of rocks and vacuum and radiation. She said it not as a sentiment, but as a geological observation. Earth, from the perspective of everything outside it, is an extraordinary exception. Its atmosphere, its liquid water, its magnetic field, its moderating oceans, its thin layer of biology that has been actively altering the chemistry of the entire planet for billions of years. All of it. Exceptionally, improbably, fortunately there. You don't know how improbable it is until you watch it disappear behind a place that has none of it. There is a geopolitical context to everything Artemis II saw on the far side that doesn't appear in the mission highlights, but shapes why NASA and the United States government committed to returning humans to the Moon when they did, at the pace they did with the resources they committed. China has already been there. Not just to the Moon, to the far side. In January 2019, China's Chang'e 4 lander touched down inside Von Karman crater, a 186-kilometer-wide impact feature at the floor of the South Pole Aitken Basin, the same basin whose buried metallic mass the Artemis II crew flew over. It was the first soft landing on the far side in the history of spaceflight. Achieving it required a relay satellite called Queqiao, parked in a halo orbit beyond the Moon to maintain communication with Earth, because direct radio contact with the far side is impossible. China built the infrastructure to land there, and did it. The U-2 rover that Chang'e 4 deployed found something significant: minerals from the lunar mantle, olivine and pyroxene, rock types that originate deep below the crust, sitting exposed on the basin floor. The South Pole Aitken impact was so large and so deep that it excavated material from hundreds of kilometers below the surface. Material that has never been exposed on the near side is sitting on the surface of the far side basin. U-2 found it and confirmed it. In 2024, China went further. Chang'e 6 landed on the far side, collected surface samples, and returned them to Earth, the first time material from the Moon's hidden hemisphere had ever been brought back for laboratory analysis. Scientists are still working through those samples. What those rocks will reveal about the Moon's geological history, and about the differences between the near and far sides that have never been directly sampled before, will take years of full analysis. This matters for Artemis because the Moon's south polar region, where ice deposits exist in permanently shadowed craters, and where Artemis III plans to land, is also where China's future crewed missions are aimed. 2 space programs, both technically capable, both with legitimate scientific interests, both directing their next human missions toward the same geography on the same planetary body. The far side's radio silence, the fact that it is permanently shielded from Earth's electromagnetic noise by 3,400 kilometers of solid rock, makes it the most valuable location in the inner solar system for certain kinds of astronomy. Low-frequency radio telescopes placed on the far side could detect frequencies below 30 megahertz that Earth's ionosphere completely blocks, opening a window into the cosmic dark ages, the period before the first stars formed that has never been available to any instrument. The quiet of the far side is not just an observation curiosity. It is a resource. Whoever establishes infrastructure there first will have significant influence over how it's used. None of this means the Moon is about to become a conflict zone. The Outer Space Treaty prohibits national appropriation of celestial bodies, but it does not prohibit operational control of specific sites or infrastructure. The Artemis II crew's far-side observations, what they described, what the geological data they collected will reveal, what the photographs still being downlinked will show, are part of a larger story about why the Moon matters now, in this specific decade, in a way it hasn't mattered since the 1960s. Not just scientifically. The question of who understands the Moon's far side and who has operational presence there is already being answered incrementally by every mission. Artemis II was one answer. There is something about this mission that hasn't been asked directly in the official press conferences. A question that is present in the historical record, but hasn't been put to the Artemis II crew specifically. Not yet. To understand why it matters, we have to go back to 1969. May 1969. Apollo 10. Apollo 10 was the dress rehearsal for the moon landing. Thomas Stafford, John Young, and Eugene Cernan flew to the moon, entered lunar orbit, undocked the lunar module, dropped it to within 15 kilometers of the surface, and came back. Everything Apollo 11 would do 2 months later, except the actual landing. It was supposed to be the routine part. When the spacecraft passed behind the moon and entered the far side blackout, the onboard voice recorders kept running. The crew was doing what crews do, managing systems, making observations, talking to each other. And then, at some point during the blackout, a sound started coming through their headsets. They described it on the recording as outer space-type music, an oscillating, whistling tone, rising and falling. Something that by the rules of physics as they understood it, in a place where no radio signal from Earth could reach, should not have been there. On the tape, you can hear the moment of recognition. You can hear them asking each other if they're really hearing it. You can hear one of them say, "Shall we tell them about it?" and another hesitate. They did not tell anyone, not in the debrief, not in the official mission report. They buried it. The transcripts were eventually declassified in 1973. The audio went onto NASA's servers in 2012. Almost nobody noticed until 2016, when it became public knowledge for the first time. When the Apollo 10 crew was asked, decades later, why they said nothing, they were afraid of being grounded. In 1969, NASA had a standing policy that any astronaut who reported a hallucination, an unexplained perception, or any sign of psychological abnormality could be removed from flight status permanently. Permanently. A decade of training ended in a meeting with a flight surgeon. Apollo 9 astronaut Rusty Schweickart had admitted to motion sickness in orbit and paid for that honesty with the rest of his spaceflight career. The Apollo 10 crew did the math. 3 men who had just heard something they could not explain, in a place where nothing should have been audible, decided that the cost of telling the truth was too high. They carried it alone. Here is the detail that complicates the story further. Apollo 10 was not the only crew that heard it. Michael Collins, alone in the command module Columbia during Apollo 11 while Armstrong and Aldrin descended to the surface, heard the same thing. He wrote about it in his memoir, Carrying the Fire, described it as a strange noise in his headset, an eerie hooing sound. The difference was that Collins had been briefed. By the time Apollo 11 launched, NASA technicians had worked through the Apollo 10 recordings and had an explanation ready, and they gave it to Collins before he climbed into the capsule. "Had I not been warned about it," Collins wrote, "it would have scared the hell out of me." The most famous solo astronaut in history, orbiting the moon alone while his crewmates walked on the surface, heard exactly what Apollo 10 heard. And the only thing that kept him calm was being told in advance. The official explanation, once the story eventually forced its way into public discussion. The command module and the lunar module were flying in close proximity, each running its own VHF radio system on similar frequencies. When 2 transmitters operate near each other on close frequencies, they can produce a beat tone, an oscillating interference that sounds to a human ear like a whistling musical note. Clean physics, straightforward engineering, and almost certainly correct. Apollo 8, the first crewed mission to lunar orbit, flew to the moon with no lunar module aboard. It was a command and service module only, with 1 VHF radio system, not 2. Apollo 8 did not hear the whistle. The one flight that removed the second transmitter removed the sound. That is as clean a piece of evidence as you're likely to find for the interference theory. But not everyone in the program accepted it completely. Al Worden, the Apollo 15 command module pilot, said years later that the Apollo 10 crew knew exactly what their equipment sounded like, and if they heard something unusual, there was probably something unusual to hear. Eugene Cernan, the last man to walk on the moon, was asked about the sound decades later, and was careful. He said he didn't remember it frightening him at the time. He did not say he knew what it was. Now, April 6, 2026, Artemis II flew the same stretch of sky. They had longer in the far side blackout than any Apollo crew. They went further from Earth than any human ever had. Their capsule carried the most sophisticated recording equipment ever flown past the moon on a crewed mission. What has the Artemis II crew said about the sound? Nothing. Not yet. Not directly. They have talked about the eclipse. They have talked about the Earth set. They have talked about the flashes and the craters and the color variations and the moment they named a crater for Wiseman's late wife. On the specific subject of whether they heard anything unusual in the far side silence, they have said nothing. There are two ways to read that silence. The first is the simplest. Orion runs on completely different hardware than the Apollo Command and Service Module. Its communication systems are digital, not analog VHF. The architecture that produced the Apollo beat frequency interference isn't present in Orion, and with no source for the tone, there was no tone. Case closed. The absence of a comment about it is simply the absence of something to comment on. The second reading is more patient. The mission has been back for only days. The crew has been through 10 days in deep space, a far-side blackout, a 54-minute solar eclipse, 6 micrometeorite impact observations, a heat shield re-entry that the entire aerospace community was watching to see if it held, a splashdown, and an immediate post-recovery medical evaluation. There are things from this mission that will take months to process and years to fully understand. The Apollo 10 crew took 40 years. There's a particular psychology to what happens when astronauts return from significant missions. The first days are medical evaluations, debriefs, press conferences, the managed public presentation of an event that took years to plan and 10 days to execute. The astronauts are still in the institutional structure of the mission, still speaking in the voice of the program, still being careful with their language in ways that are completely appropriate and completely genuine. They are professionals. They choose their words. What they eventually say to historians, to biographers, to the interviewers who sit with them years later when the institutional pressure has eased, is sometimes different. Not contradictory. The facts are the facts, but richer, more textured. The parts that didn't fit neatly into the official account start to surface. Not because anyone was lying, but because the full account of an extraordinary experience requires distance that can only come with time. Michael Collins wrote Carrying the Fire, his extraordinary account of the Apollo 11 mission, several years after returning from the moon. The precise description of the sound in his headset was in that book. Not in the post-mission debriefs, not in the press conferences, in the memoir. Written with the care of a man who had time to think about what he'd experienced and decide how to describe it. Eugene Cernan, who walked on the moon during Apollo 17 and was the last human to do so, gave interviews for decades about the experience. His public statements about the Apollo 10 sound evolved over time. In early interviews, he was dismissive. A hardware artifact, nothing more. In later interviews, he was more careful. He'd say he didn't remember being frightened. He'd stop short of saying he knew exactly what it was. The careful stop short of a man who'd been there and wasn't quite done thinking about it. The Artemis II crew will write books. They'll give interviews 5 years from now and 10 years from now. They'll sit with the specific experience of 40 minutes on the far side of the moon in a way that no press conference schedule allows. And what they eventually say about all of it: the silence, the flashes, the geology, the Earth set, the eclipse, the sounds, if there were sounds, or the deliberate absence of them, will be the complete account. Right now, we have the beginning of it. The policy that frightened Stafford, Young, and Cernan into silence has officially been retired. NASA now tells astronauts explicitly that anomalous observations are scientific data, not disqualifying events. Whether that policy holds when a specific astronaut with a specific career at stake has to actually make the call, in public, about something that will attach to their name forever, that is a question that has never really been tested in public. What we know is that 4 people went somewhere no human had been in 53 years, went further from Earth than any human in history, spent 40 minutes in a silence more complete than any astronaut before them, and came back with most of the photographs still undownloaded from the capsule storage systems because the bandwidth between deep space and the ground isn't fast enough to have sent everything yet. The full record of what those 4 people saw and heard and experienced behind the moon, every frame of every camera, every second of every audio recording, every reading from every instrument, is not fully public yet. What the Artemis II crew will eventually say, and what the instruments will eventually confirm, is something we'll be learning for years. For now, let's hold what we have. 4 people who went where humans hadn't been in half a century, who flew over a buried metallic mass and warm granite that shouldn't exist, and magnetic swirls whose explanation still isn't fully settled, who watched Earth set behind a world with no atmosphere and no mercy, and described it as a reminder of everything that makes home, home, who were alone for 40 minutes in a silence that no training fully prepares you for, flying over the most ancient and battered landscape in the solar system, while Mission Control held their stations and waited, who saw 6 flashes of light on the dark surface below them, micrometeorites hitting rock that has no protection against them, and whose observations of those flashes will inform where and how future humans build the structures that will keep them alive. There's one more thing that happened during the mission that belongs in this account. Not a technical event, not a geological observation. Something quieter. 4 days before splashdown, while Orion was still outbound, after the lunar flyby, after the Earth set, after the far side blackout, after the eclipse and the flashes, the crew requested something from Mission Control. They had identified 2 features on the far side that they wanted to name. Informal names, not yet submitted through the official International Astronomical Union process, but real names that the crew was putting on record. One feature they named Integrity, after the name they had given their Orion capsule. The other was a small, bright crater sitting on the boundary between the near side and far side of the moon. The boundary between the hemisphere humans have watched for millennia, and the hemisphere we are only beginning to explore. They named it Carol. Hansen told Mission Control why. He said it was a bright spot on the moon. Visible from Earth, he said, during certain phases of the lunar cycle, if you know where to look. Wiseman's late wife, Carol Taylor Wiseman, who died at 46 from cancer, who told him not to quit, who told him this is where you work and you love your job, and we should not give that up for this, whose 2 daughters he raised alone, who were on the ground when their father launched on the most dangerous mission in a generation, who will grow up knowing that there is a small bright spot on the moon named for their mother. Mission Control said nothing for 45 seconds after Hansen's request. 45 seconds of silence on a mission communication loop is an enormous pause. These are channels that exist to transmit information, to confirm procedures, to maintain the operational rhythm of a crewed spaceflight. Silence on them is conspicuous. It means the people on both ends of the connection are doing something other than transmitting. What they were doing, 252,000 miles apart, was the same thing. The crew, named Two Features, on the boundary between the side of the moon humans have watched for all of human history, and the side we are only beginning to understand. One they named for the spacecraft that carried them. One they named for a woman who never went to space, who never saw the moon up close. Who told her husband not to let her illness stop him, and then died before she could find out whether that advice was the right thing to give. The crater called Carol sits on that boundary, the near side and the far side, the known and the unknown, the visible and the hidden. A small bright spot that the crew said is visible from Earth during certain phases of the lunar cycle, if you know where to look. The mission brought 4 people to the moon and brought them back. It set a distance record. It made history with its crew composition. It generated geological observations that will take years to fully analyze. It tested a spacecraft that had never flown people before, and a heat shield that had previously failed, and a re-entry trajectory that had never been flown crewed. It contributed to the biological dataset that will eventually tell us whether it's possible to send humans to Mars without killing them through accumulated radiation damage. It did all of these things, and it named a crater for a woman who asked one person she loved not to stop. That is also what the mission was. Then they came home. To understand what happened during Artemis II's re-entry, you have to understand what happened during Artemis I. Not just the headline version, the technical detail that almost nobody was talking about publicly until the crew had already launched. In November 2022, NASA flew Artemis I, an uncrewed Orion capsule on a 25-day journey around the moon and back. By nearly every measure, it was a success. The launch worked. The trajectory worked. The spacecraft orbited the moon, made all its planned burns, and came home. Mission controllers celebrated. Then the engineers got the capsule back to Kennedy Space Center and took the heat shield apart. Over 100 locations showed unexpected damage. Large sections of charred avcoat, the ablative heat shield material that Orion was depending on to protect the crew, had cracked and broken away in irregular chunks. Not the controlled, even ablation that decades of ground testing had predicted. Jagged, unpredictable material loss that had in some areas exposed layers of the shield that were never supposed to encounter re-entry temperatures directly. Avcoat is an ablative material. It is engineered to destroy itself on purpose. As the spacecraft slams into the upper atmosphere at hypersonic speeds, the outermost layer chars under the extreme heat. That charring absorbs enormous amounts of thermal energy. The char then erodes away into the airstream, carrying the absorbed heat with it. Layer by layer, the shield sacrifices itself so the structure underneath stays cool enough for the crew to survive. NASA used Avcoat on every Apollo command module that brought astronauts home from the moon. It worked flawlessly every single time. But the Orion shield was manufactured differently from the Apollo shields. The original Apollo heat shields were a single honeycomb structure, containing roughly 320,000 tiny hexagonal cells, each one filled by hand with Avcoat material. Painstaking work that took months. For Orion, Lockheed Martin simplified the process. Instead of filling hundreds of thousands of individual cells, They manufactured approximately 186 pre-machined avcoat blocks, each designed to fit a specific position on the heat shield's 5-meter-wide carbon fiber skin. The blocks are bonded into place like pieces of a puzzle. It saved enormous amounts of time and manufacturing complexity. Whether it preserved the same thermal performance was a question nobody could answer until the shield flew. And then it flew, and the answer was complicated. The damage pattern on Artemis I correlated with something specific about the re-entry technique that mission used. Artemis I flew what engineers call a skip re-entry. The capsule first dipped into the upper atmosphere to shed velocity through aerodynamic drag, then used its lift to skip back above the atmosphere like a flat stone bouncing off a pond, then dipped back down for a final descent. The advantage was precision landing location flexibility. Inside the avcoat, it was a disaster. During the skip phase, when the capsule briefly climbed back above the atmosphere and external heating dropped, something went wrong in the shield's chemistry. Avcoat produces gases internally during ablation, essentially burning from within. Under sustained high heat, those gases normally vent outward through the porous char layer. But when heating paused during the skip, the char layer became denser, less porous. The avcoat underneath was still warm enough to keep producing gas. That gas had nowhere to go. Pressure built inside the blocks, and when the capsule plunged back for its second and final pass, those pressurized pockets ruptured, blowing charred material off the shield in chunks. There is a detail in the investigation that doesn't get talked about enough. Even with over 100 locations of unexpected char loss, the temperature inside the Orion cabin during Artemis I never exceeded the mid-70s Fahrenheit. The thermal performance exceeded expectations. The avcoat was doing its job blocking heat. The problem was that the material was tearing itself apart while doing it, and nobody could predict where or how much would come off next. An ablative shield with unpredictable ablation is something like a parachute that opens but might have random holes in it. It will probably slow you down. You just cannot be certain by how much. NASA did not replace the heat shield for Artemis II. The shield was already built, already bonded to the crew module, and replacing it would have added years to a program that had already slipped from 2024 to 2025 to 2026 through a cascade of technical delays, weather disruptions, and hydrogen leaks during dress rehearsals. Jared Isaacman, the NASA administrator who has personally flown to orbit aboard a SpaceX Dragon, reviewed the data and accepted the plan to fly as is. Instead of rebuilding, NASA changed the flight plan. The skip re-entry was eliminated entirely. Orion would fly a steeper, more direct descent, hitting the atmosphere harder but for a shorter duration, with no pause in the middle where trapped gases could accumulate and fracture the shield from within. The trade-off was significant: higher G-forces on the crew, greater structural loads on the vehicle, more intense peak heating, a less flexible splashdown zone. But the gas pressure problem that destroyed the Artemis I shield would not have the opportunity to develop. NASA tested avcoat samples under the modified profile conditions in refurbished ArcJet facilities at Ames Research Center. They modeled scenarios where the heat shield lost far more material than Artemis I had experienced. And in every simulation, cabin integrity held. The risk estimates were not comfortable. NASA's own assessment for overall mission risk fell somewhere between 1 in 2 and 1 in 50, depending on which portion of the uncertainty range you accepted. At the optimistic end, a roughly 2% chance of crew loss. At the other end, a coin flip. NASA's official threshold for acceptable risk on Artemis missions is 1 in 30. Former NASA aerospace engineer Charles Kamada, who worked on the Columbia investigation and spent years studying heat shield failure modes, told interviewers that he estimated the probability of heat shield failure at roughly 1 in 20, a 5% chance that the 4 people inside the capsule would not make it home. He was not speaking officially. He was speaking as someone who had read every report, run his own analysis, and was not willing to pretend the numbers looked better than they did. 5% is not the same as 50%. It is not even the same as 10%. But for 4 specific people with names and families and careers and the specific weight of everything they represented, 5% is not an abstract number. It is a real, measurable probability that they would die. Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen reviewed the heat shield investigation. They saw the photographs of the Artemis I damage. They studied the modified descent profile, the risk numbers, the test data. They understood what 1 in 20 means when you are the one inside the capsule. They flew anyway. 6 days after the far side flyby, after the eclipse, after the blackout, and the impact flashes and the Earth set. After the crater was named, and the photography was done, and the bone marrow chips were still running their biological experiment on the wall of the capsule, it was time. April 10th, 2026. The Pacific Ocean, west of San Diego. The Orion spacecraft's European-built service module separated from the crew module approximately 20 minutes before re-entry interface. The service module, which had provided propulsion, power, water, and breathable air for the entire 10-day mission, broke away and fell behind. It would burn up in the upper atmosphere on its own trajectory, not even reaching the lower atmosphere intact. Everything disposable gets jettisoned before re-entry. One by one, over the course of the mission, every major component of the 30-story rocket that launched 4 people from Florida had been discarded. The solid rocket boosters, the core stage, the interim cryogenic propulsion stage, the launch abort tower, the service module, all gone. What remained was a capsule roughly the size of a large SUV, falling alone toward a planet. Orion entered the atmosphere at approximately Mach 33, 33 times the speed of sound, roughly 25,000 miles per hour. For context, a capsule returning from the International Space Station re-enters at about Mach 25. The additional velocity required to return from lunar distances adds roughly 15% more speed at atmospheric interface. And because kinetic energy scales with the square of velocity, that 15% more speed means dramatically higher heating rates, dramatically higher aerodynamic loads, dramatically more demanding conditions for every system on the vehicle. At those velocities, the air in front of the capsule cannot get out of the way. It compresses into a shock wave, superheats, and ionizes into plasma. The temperature on the face of the heat shield climbs past 2,760 degrees Celsius. Hotter than structural steel melts. Hotter than titanium fails. Hot enough to vaporize exposed aluminum before the brain could register what was happening. The only thing standing between 4 people and that plasma was a 5-meter-wide mosaic of 186 blocks of avcoat, designed to burn at a precisely controlled rate. On the crew module windows, the view went white, not the white of cloud cover or diffuse light, the white of plasma sheeting across every surface, the atmosphere itself on fire from the violence of the entry. Wiseman later described the glow coming through the windows as something that didn't look like anything he had a reference for. not flames in the ordinary sense. Something older and more absolute. The crew felt the G-forces mount. The new direct entry profile was harder than the skip entry would have been. The peak deceleration was close to 3.9 Gs, nearly 4 times the force of gravity pressing them into their seats. For bodies that had spent 10 days without any gravitational load at all, that transition was violent. The heart that had been shrinking in microgravity suddenly had to pump against nearly 4 times normal gravity. The fluids that had pooled in the upper body came crashing down. The vestibular system, recalibrated over 10 days to a world with no reliable gravitational reference, was overwhelmed with input all at once. They heard the atmosphere ripping apart around the capsule, and in Houston, the screens went blank. The plasma sheath absorbs and reflects radio waves across virtually every usable frequency band. No signal gets in, no signal gets out. For approximately 6 minutes during peak heating, Rick Hendling, the lead entry flight director, and every flight controller in mission control sat at their consoles staring at screens that showed nothing. They had trained for this. Simulations had made the silence familiar in a procedural sense. Simulation cannot make it familiar in the way that matters. What you are sitting with in those 6 minutes is the knowledge that you cannot do anything, that whatever is happening inside that capsule is happening without you, that the engineering either works or it doesn't, and you will find out when the signal comes back, and if the signal doesn't come back, you will find out that way too. This particular quality of helplessness, the absolute inability to intervene, to help, to even know, is one of the specific weights that mission controllers carry and that the public rarely thinks about. The astronauts face physical risk. The people in Houston face a different kind. The knowledge that they sent those 4 people into that capsule, that they reviewed the heat shield data and accepted the risk, that they will be the first to know what the decision cost. In April 1970, the crew of Apollo 13 re-entered after their service module was crippled by an oxygen tank explosion. Nobody knew if the heat shield on the command module had been compromised by the blast. The expected blackout was 3 minutes. It stretched past 4, past 5, past 6. Gene Kranz and his team sat in total silence. When Charlie Duke finally heard Jack Swigurt's voice cut through the static, the room broke. In February 2003, the Columbia orbiter broke apart during re-entry because a piece of foam had struck the thermal protection tiles on the wing's leading edge during launch, and nobody caught it in time. The crew never received a warning. Mission Control didn't know until the telemetry vanished and never came back. Heat shield failure during re-entry is not a theoretical risk. It has killed 7 people. There is a specific and uncomfortable parallel between the Columbia situation and the situation Artemis II flew into that the Columbia Accident Investigation Board would have had hard questions about. Columbia's fundamental failure was not the foam strike. It was NASA's organizational culture. The CAIB described it as normalization of deviance, a process by which an organization gradually redefines anomalies as acceptable through repeated exposure to them without immediate consequence. Foam had been striking the orbiter's thermal protection on previous missions. It hadn't caused a catastrophic failure yet, and so it became accepted, until it did. The Artemis I heat shield damage was an anomaly. It was unexpected. It was not fully understood at the time Artemis II flew. The people who made the decision to fly knew this. They had a specific mitigation strategy. They had tested it, they had run the models, they had explicit risk numbers on paper, and they had 4 people who had read those numbers and chosen to fly. Whether that is categorically different from what preceded Columbia, or whether it is the same organizational process wearing better documented clothes, is a question that will be debated by safety researchers for as long as the program runs. The people inside the program are convinced of the former. They have reasons for that conviction. History will determine whether the conviction was warranted. This was what Rick Henling and his team were sitting with for 6 minutes. Not just uncertainty about whether the modified profile worked. The weight of what it means to be responsible for 4 people in a vehicle with a known and incompletely understood anomaly, on the basis of a mitigation strategy that had been validated in ground testing and computer simulation, but never in the actual operational environment, until today. The weight of the history of every time someone sat in a mission control room while the telemetry went dark and did not come back. The clock ran. The screens showed nothing. Then, at 8:07 p.m. Eastern Time, the signal came back. The drogue parachutes had deployed. The main canopies opened in sequence. The capsule was descending. The crew was alive. The heat shield had held. When the post-splashdown photographs came in, engineers examining the shield noted divots, cracking, signs of uneven ablation, not identical to Artemis I, not as severe, but present. The new direct entry profile had significantly reduced the gas pressure problem. The shield had not failed, but it had not behaved perfectly either. The investigation that follows every re-entry had new data to work with. Howard Hu, the Orion program manager, described the shield performance at the post-splashdown press conference with the specific, careful language of someone who is being honest about complexity rather than managing a narrative. They'd done it. The crew was home. The shield needed to be redesigned for future missions. Both things were true simultaneously. The crew was extracted from the capsule in open water, transferred to an inflatable raft, and helicoptered to the USS John P. Murtha. They walked under their own power. Let's talk about what those 10 days did to 4 people that the photographs from the recovery couldn't show. The changes started within hours of launch. Not days, hours. The moment the Space Launch System's engines cut off on April 1st and the crew reached orbit, gravity stopped pulling their blood and body fluids downward. On Earth, roughly 2 liters of fluid sit in your legs at any given moment, held there by gravity. Remove the gravity, and that fluid has nowhere to go but up. It floods into the chest and the head almost immediately. The face swells, the sinuses clog, the legs thin out. Astronauts have a name for this that sounds almost funny until you think about what it actually describes. Puffy face, chicken legs. Within a few hours of reaching orbit, all 4 crew members would have looked noticeably different from their launch day photographs. Swollen cheeks, narrowed eyes, congested noses. Their legs shrinking as fluid drained out of them. If you had seen a photograph of any one of them on day 3 next to their official crew portrait, you would have thought they were sick. They weren't sick. Their bodies were doing exactly what they're built to do, adapting to their environment. The problem is that the environment was lying to them. Your cardiovascular system evolved over hundreds of millions of years to solve one specific problem: pumping blood uphill against a constant gravitational pull. Your heart, your veins, your arterial valves, your leg muscles, all of it is calibrated to fight gravity every second of your life. Take that gravity away, and the system doesn't break. It recalibrates. Your heart, suddenly having no hill to pump against, begins to shrink, not from disease, from efficiency. A smaller heart is all you need when there's no resistance. Your body, in its ruthless pragmatism, starts downsizing the one organ you cannot afford to lose. On a 10-day mission, the shrinkage is measurable but modest. On a 6-month mission aboard the International Space Station, it becomes a serious medical concern. The Artemis II crew was in the window, where the process had started, but hadn't reached a dangerous threshold. The danger would come on the ground, when that shrunken heart suddenly had to pump against full Earth gravity again. Against nearly 4 Gs during re-entry, and then against normal Earth gravity the moment they were standing on the ship's deck. This is why recovery teams were waiting in the Pacific for a reason other than rescue from drowning. The crew was not simply being retrieved. They were being medically managed through a physiological transition that their bodies had not yet completed. Bone followed a similar logic. Bone is not the dead scaffolding most people imagine. It is a living tissue constantly being torn down and rebuilt by 2 types of cells working in opposition. Osteoclasts dissolve old bone. Osteoblasts lay down new bone. On Earth, the balance between these two is maintained by mechanical stress, the weight of your own body pressing down on your skeleton every time you stand, walk, or climb a flight of stairs. That stress tells your bones to stay strong. Remove the stress, and the osteoblasts slow down, because there is no demand for new construction, while the osteoclasts continue dissolving at their normal rate. The result is a net loss of roughly 1 to 1.5% of bone mineral density per month, concentrated in the weight-bearing bones of the hips, spine, and legs. That rate is roughly equivalent to what a postmenopausal woman with osteoporosis loses in an entire year on Earth, compressed into 30 days. 10 days isn't long enough for catastrophic bone loss. The crew didn't come home with brittle femurs, but measurable changes at the cellular level begin within 72 hours. The biological clock of bone remodeling had already been reset before the first week was done. The radiation dimension of what Artemis II did to the crew's bodies is the one that goes furthest beyond the mission itself. The International Space Station orbits inside Earth's magnetosphere, the magnetic bubble that deflects most of the high-energy particles streaming in from the sun and from deep space. It's not perfect protection, but it's substantial. The Artemis II crew left that bubble. They flew through the Van Allen radiation belts on the way out, and again on the way back. Regions where trapped electrons and protons swirl at tremendous energies. And for the days between Earth and the Moon and on the far side, they were exposed to the full deep space radiation environment with nothing between them and incoming particles, but the aluminum and composite walls of the Orion capsule. The total dose for the 10-day mission was modest by career astronaut standards, roughly equivalent in immediate biological terms to a full-body CT scan. That sounds manageable, and for a single mission it is. The concern isn't what one CT scan does to you. It's what this exposure reveals about the longer missions that must follow if the Artemis program succeeds. Galactic cosmic rays include heavy ions, atomic nuclei stripped of their electrons and accelerated to enormous speeds by supernovae and other catastrophic events throughout the galaxy. These particles punch through shielding and through human cells in ways that low-energy radiation does not. A single heavy ion can tear through a cell like a bullet through paper, shredding DNA in ways the cell's repair machinery may struggle to fix cleanly. The damage isn't always lethal to the cell. Sometimes, the cell survives with errors in its genetic code, and those errors can accumulate over time into something that develops over years or decades. This is the radiation exposure the Artemis II crew accepted, not a dose that will visibly affect their health tomorrow. A dose that will be tracked in their medical records for the rest of their lives. Mounted on a wall inside the Orion capsule during the mission were a set of small devices about the size of USB thumb drives. Each one contained living human bone marrow, grown from cells donated by the astronauts themselves before the flight. The experiment was called Avatar, a virtual astronaut tissue analog response. Scientists at Harvard's Wyss Institute had taken platelet samples from 3 of the crew members, extracted bone marrow stem cells, and cultivated them onto organ-on-a-chip devices that replicated the structure and function of human bone marrow. These chips flew the same trajectory as their human donors, absorbing the same radiation, experiencing the same microgravity for the entire 10-day mission. Twin chips remained on the ground as controls. Bone marrow was chosen deliberately. It's one of the most radiation-sensitive tissues in the human body. It produces red blood cells, white blood cells, and platelets. Damage it, and you compromise the immune system, the blood's ability to carry oxygen, and its ability to clot. When the chips returned to the lab, researchers began performing single-cell RNA sequencing to map how thousands of individual genes changed during the flight. The results will be compared to the ground controls and to blood samples taken from the actual astronauts before and after the mission. Nobody expects the Artemis II crew to show signs of radiation sickness. The dose was too low for that. What researchers are looking for is subtler, molecular signatures of stress, early indicators of accelerated aging in the cells, changes in gene expression that might, over a longer mission, cascade into something clinically significant. The Avatar chips are a preview, a way to see the future of deep space travel written in the biology of 4 people who spent 10 days living in it. The data will inform countermeasure development, pharmaceutical interventions, personalized exercise protocols, shielding strategies for the missions that follow. In a very specific and literal sense, the biology of the Artemis II crew is still at work, right now, in the laboratories processing those chips. Still contributing to the mission, still yielding data weeks after the capsule hit the water. This is a detail that gets folded into mission summaries under the word science. It deserves more attention than that. 3 members of the Artemis II crew essentially donated fragments of their own biological identity, cells that carry their personal genetic information, their individual sensitivities, their specific vulnerabilities, to be exposed to the most hostile environment any human has voluntarily entered in over 50 years, so that the people who come after them might survive it better. That is what the mission was, in part. Not just exploration, an act of deliberate biological sacrifice for people they'll never meet. There's another dimension of the crew's biology that the post-mission analysis is examining, and that almost nobody discusses in general coverage: what the mission did to their immune systems. And specifically, what it may have woken up. Spaceflight suppresses the immune system. The exact mechanisms are still being studied, but the pattern is consistent across decades of astronaut medical data. Astronauts get sick more easily in space. Their wounds heal more slowly, and viruses that have been dormant in their bodies for years, latent herpes viruses particularly, sometimes reactivate under the combined physiological stress of microgravity, confinement, radiation, and altered sleep patterns. The Epstein-Barr virus, varicella zoster, which causes chickenpox and shingles, and other herpes family viruses are extraordinarily common in the general population. The immune system in healthy people keeps these viruses suppressed, inactive, essentially locked. Under normal immune function, they cause no symptoms and present no threat. Under suppression, they can reactivate. The Artemis II crew participated in an immune biomarkers investigation during the mission, blotting saliva onto specialized paper booklets, since Orion had no refrigeration for biological samples. Those samples are being analyzed now for evidence of viral reactivation. Not because anyone expects the crew to be sick. They're not. But because the data will tell researchers whether 10 days of deep space exposure was sufficient to begin the same immune suppression pattern observed on longer missions. For a 10-day mission, the immune effects are limited. For a 6-month Mars transit, they would not be. An astronaut halfway to Mars, immune suppressed, with a reactivated virus and no possibility of evacuation, is a specific medical scenario that the space medicine community is actively working to prevent. The Artemis II crew's saliva samples are part of the dataset that informs that prevention. Each crew member also wore wrist-mounted actigraphy devices throughout the mission, essentially sophisticated fitness trackers that recorded their movement, sleep cycles, and rest activity patterns in real time. Sleep quality in a capsule barely large enough for 4 people to sleep, eat, and work without bumping elbows is not a given. The constant hum of life support systems, the absence of a natural day-night cycle, the knowledge that you are farther from home than any human has ever been, all of it compounds. About 70% of astronauts report headaches in space, even those who never get them on Earth. The likely culprit is a combination of elevated intracranial pressure from fluid shifts and slightly elevated carbon dioxide levels in the cabin atmosphere. A headache you cannot escape in a room you cannot leave, while floating in a place where the nearest hospital is 250,000 miles away. That is not just a medical issue. It is a psychological one. ARCA, the Artemis II crew autonomous research and collaboration assessment, monitored the crew's teamwork dynamics, cognitive performance, and stress levels throughout the mission. 4 people in a space the size of a camper van, performing complex technical tasks while their bodies silently reconfigure themselves, represents a psychological pressure that no training environment can fully replicate. What the data from those monitoring systems reveals will shape the crew's selection, training, and mission design criteria for every subsequent deep space mission. Christina Koch had been here before in one sense. She spent 328 days on the ISS in 2019 and 2020. She knows what microgravity does to a body over months. For her, 10 days was a sprint. For Wiseman, who had done 6 months on the station but never deep space. For Glover, who had also done a long ISS tour. And for Hansen, who had never been to space before this mission. The experience of what their bodies were doing was new in the specific, deep way that direct experience is always different from intellectual preparation. Hansen had spent a week living underground in an Italian cave as part of psychological preparation for isolation and confinement. The cave helped with the enclosed space. It could not prepare him for what it feels like when the radiation environment is measurably changing your cellular biology in real time, and you are more than 250,000 miles from the nearest doctor. Victor Glover has given several interviews since returning from the mission, and in them he has been characteristically precise. Not poetic for its own sake. Precise. The specific precision of a person who understands that his words will be interpreted and is choosing them carefully to be accurate. He described the far side of the moon as not what you expect when you expect a grey ball. He talked about the color, the subtle browns and the hints of blue in certain regions that cameras flatten into uniform grey. He described the Terminator as full of magic, with islands of light, surrounded by darkness that had genuine visual depth to it, like you could fall through the shadow to the center of the moon. And he said the view from the eclipse, the solar corona, ringing the entire lunar limb, the complete halo of the sun's outer atmosphere glowing around the edge of the dark disk, was probably beyond what human beings had evolved to see. That phrase has been quoted and noted, but rarely unpacked. It deserves unpacking. The human visual system evolved in an environment of certain scales and certain light sources. It evolved on a planet where the brightest natural object in the sky is the sun, where the largest structure in most visual fields is the horizon, where the most complex illumination effects arise from weather and terrain. It evolved for a world of bounded scales, the furthest horizon, the highest mountain, the widest ocean. The brain developed aesthetic and emotional responses to visual experience within those bounds. Grandeur, in the human neurological sense, has a scale limit. There is a point beyond which the human brain cannot fully process what it is looking at as a unified experience, and instead generates the fragmentary, overwhelming sensation that people throughout history have called sublime. Glover is saying that the view from behind the moon, the complete corona, the Earth-sized shadow, the far-side terrain passing below, the total absence of any reference scale that would locate the observer relative to what they were seeing, exceeded the scale at which his visual system could integrate what it was seeing into something his brain knew how to feel about. It was bigger than his experience had given him the tools to experience. This is not a metaphor. It is an honest neurological description of what the mission was. Let's stay with Glover for a moment longer, because what he represents in the context of human spaceflight history is something that deserves more than a footnote in the mission summaries. Victor Glover became, on April 6, 2026, the first black astronaut to fly beyond low Earth orbit. He is the 57th human being to have reached the moon's vicinity. The first 56 were all white. All were male except for Christina Koch. The demographic reality of who has been to deep space, who has seen the Earth from a distance sufficient to see its shape, who has experienced the overview effect in its most extreme form, who has had the view that Glover described as beyond what human beings evolved to see, was, for the entire first 53 years of deep space exploration, a very specific and narrow slice of humanity. What that costs is genuinely hard to quantify. We can enumerate the practical barriers, institutional racism in the military flight programs that historically fed NASA's astronaut corps, the deliberate exclusion of women from the early astronaut selections, the political and budgetary decisions that ended deep space crewed missions for half a century and kept human spaceflight confined to low Earth orbit where diversity programs could operate. But the truly extreme frontier remained accessible to almost no one. We can enumerate these things without being able to fully measure what it meant that the view from the far side of the moon was inaccessible to most of the people on the planet, not because of any limitation in their capability, but because of who they were. Glover is not naive about any of this. He has spoken in interviews before and after the mission, with the specific, careful weight of someone who knows his words will be used as evidence in arguments he did not choose to start and whose terms he does not fully control. He is not a symbol who happens to be a person. He is a person who has been made into a symbol and who is navigating that with considerable grace. What he said after the mission about the corona and the far side and the view was not a statement about representation. It was a statement about what he saw. The statement about representation is implicit in who was saying it, and he has let that remain implicit rather than spelling it out in ways that would flatten it. The overview effect literature that has developed around astronaut testimonies suggests that the view from deep space has a specific quality of dissolving certain cognitive structures. The neural scaffolding that maintains the distinction between self and world, between what is mine and what is everyone's, between the importance of the divisions that organize human social life and their actual significance at the scale of what the universe is. Frank White, who coined the term, documented this across dozens of interviews with astronauts and cosmonauts. The experience reshapes the person, not dramatically, not instantly, but measurably and lastingly. For 53 years, that experience was available only to a very specific demographic. The question of what it means to begin distributing it more broadly, to begin building a human record of what it's like to see Earth from the Moon, that includes the full range of perspectives that humanity actually contains, is not a rhetorical question. It is a genuinely open scientific and philosophical question about what deep space exploration is for and what it produces. Glover's photographs from the mission will be studied by scientists. His biological data will inform medical protocols. His words, recorded in the mission transcripts and in the press conferences and interviews that follow, will be read by people trying to understand what Artemis II was. And at some future date, the visual record of a black man looking at the far side of the moon through the window of a spacecraft, seeing something that no member of his community had ever seen, contributing to a record that had for 53 years been built entirely without them, will be understood as something more than a NASA milestone. It will be understood as part of the human record of what deep space exploration is, and what it costs, and what it changes about the people who go. We have been talking about Artemis II in the shadow of Apollo throughout this entire video. The comparisons are natural, and in some ways unavoidable. Both programs sent humans to the moon. Both produced extraordinary science and engineering. Both required specific kinds of courage from specific people. But there is a meaningful sense in which Artemis II proved something that Apollo never had to prove, and it's worth being precise about what that was. Apollo flew the Saturn V. The Saturn V was designed from the outset to go to the moon and return. It was engineered for exactly one mission profile: launch, translunar injection, lunar orbit, landing for the later missions, return. The Apollo Command Module's heat shield was designed for lunar return velocities and tested in exactly that role, validated across 13 flights. By the time of the final Apollo missions, the technical understanding of how that heat shield performed was substantial and well calibrated. The unknowns had been largely eliminated through successive flights. Artemis II flew with a heat shield that had failed in unpredicted ways on its first flight and had been modified in response to that failure. It flew the modification without a prior uncrewed validation flight. The specific re-entry trajectory it flew had never been flown by a crewed vehicle before. The European service module that provided propulsion and life support throughout the mission was flying its second crewed mission, Artemis II being the first crewed flight, and this being only the second. The SLS rocket itself was flying only its second mission of any kind. In this specific sense, Artemis II carried a different kind of uncertainty than Apollo carried by its later missions. Not more risk necessarily. Risk is a complicated calculation, but a different character of uncertainty. The uncertainty of learning rather than the uncertainty of the genuinely unknown. Apollo's first crewed lunar landing, Apollo 11, flew after 8 successful crewed Apollo flights. The program had accumulated an enormous body of knowledge about how its systems behaved in the actual operational environment before it asked them to carry people to the lunar surface for the first time. There were things Apollo 11 didn't know. Neil Armstrong's heart rate during the final approach, 17 seconds of fuel remaining at touchdown, a 12:02 alarm in the landing computer, an overloaded guidance system flagging errors while executing a landing in terrain that had not been fully characterized. There were real unknowns. But the basic question of whether the hardware could do what it was designed to do had been answered repeatedly before the stakes were highest. Artemis II answered a version of that same question about hardware that had failed before and been modified in response. It answered, yes, the modified entry profile solves the gas pressure problem sufficiently for crew survival. It answered, yes, the European service module can power and propel Orion across nearly 700,000 miles of round-trip travel without a critical failure. It answered, yes, the SLS and Orion together can launch a crew, execute a translunar trajectory, execute a lunar flyby, and return to Earth in a survivable re-entry. These were not questions Apollo had to answer about its own hardware, because Apollo's hardware had proven itself before the most challenging missions flew. Artemis is in a different phase of that learning curve, and Artemis II was the mission that moved the program meaningfully forward on it. What Artemis II did not prove is also worth naming. It did not prove that the heat shield design is final or fully understood. The divots in the re-entry record require investigation, and the redesign for Artemis III and beyond requires validation. It did not prove that the commercial landers will be ready when needed, or that orbital refueling at the scale Starship requires is achievable on the proposed timeline. It did not prove that 2 astronauts can safely land on the lunar South Pole and return, because nobody has tried that yet. It did not prove that a permanent lunar base is buildable on any specific timeline, because the hardware and infrastructure required for that are at varying stages of development, and none of them have been exposed to the actual lunar environment. What Artemis II proved, specifically, was that the foundational mission capability, launching people, flying them to the moon's vicinity, and bringing them home alive, is real and not just theoretical. That this particular machine, with these particular people, in these particular conditions, works. That the program can produce a mission that completes its objectives and returns its crew. That is not nothing. In the history of crewed spaceflight, it is specifically the thing that is required before everything else can follow. You cannot build a base on the moon if you cannot get people to the moon and bring them home. Artemis II proved the latter. Everything else is what comes next. There is one more dimension of Artemis II that is still unfolding as you're listening to this. The full photographic record from the mission has not been released. Over 7,000 photographs were taken during the 10-day mission, and the bandwidth between deep space and Earth's ground stations means the downlink process, transferring all of that data through a radio link from a spacecraft at increasing distance, takes time, weeks in some cases. High-priority images were processed and released quickly. The full archive is still being assembled. Within that archive are images of the far side of the moon at resolution and with illumination geometry that no orbital camera has matched. Images that will allow planetary geologists to map specific features, crater morphologies, slope angles, surface textures, shadow patterns that have been inferred from satellite data but never directly confirmed at the level of detail that a human-operated camera at close range provides. Cox, systematic photography of color variations in the regolith, the subtle browns and blues and rust tones that standard camera processing had been rendering as uniform gray, will be examined by spectroscopists trying to understand what those color differences represent chemically. Compositional variations, space weathering gradients, evidence of specific past volcanic activity. The color observations that a trained geophysicist made with her eyes may point researchers toward features in the data that would not have been flagged for examination without the human observation saying, "This is not uniformly gray, and the difference matters." The eclipse photography, a 54-minute solar totality from a position no human has ever occupied, will be examined by solar physicists studying the corona's structure at close range. The plumes and arcs and streamers visible in the corona during totality trace the sun's magnetic field lines in ways that vary over the solar activity cycle. The Artemis II eclipse occurred during solar maximum, and the corona's structure during maximum differs from its structure during minimum in ways that carry information about the sun's internal magnetic dynamics. Those photographs are data that has never been collected from this geometry before. The images of the micrometeorite impact flashes, 6 of them, millisecond duration pulses of blue-white light on the darkened lunar surface during totality, will be cross-referenced against simultaneous data from satellites in lunar orbit to establish independent confirmation of the impact locations. Each confirmed event is a calibration point for flux rate models used to design lunar surface infrastructure. The information embedded in 6 millisecond flashes observed by human eyes from a passing spacecraft will eventually appear in engineering specifications for the walls of the habitats being designed for them. South Pole Base. And somewhere in the drive still being processed, the complete visual record of 40 minutes on the far side in total radio silence will eventually be fully published. The unselected frames, the complete eclipse sequence, the full arc of the Earth set, the faces of 4 people doing their work in a quiet that has no earthly equivalent, in a landscape that had never been seen from this close by anyone alive. That record is being assembled. It will take time. Some of what it contains will be scientifically important in ways that won't be understood for years, after the photographs are in the hands of the researchers who need to study them. This is always what happens after a mission of this scale. The public event has a shape: launch, mission, splashdown. That gives it the structure of a story with a clear ending. But the scientific story that begins at splashdown has no clear ending. It unfolds over years, in laboratory analyses and published papers, and the slow accumulation of understanding that is what science actually produces. The Artemis II crew landed on April 10th. The mission continues. Jeremy Hansen's words on this mission have been chosen with an awareness that his particular position, the first non-American to leave Earth's orbit since 1991, the first Canadian ever to fly beyond low Earth orbit, carries a representational weight that he has not avoided. At the moment when Orion's telemetry confirmed that the crew had broken Apollo 13's 56-year distance record, Hansen spoke directly into the official mission record. He knew the words would be archived. He chose them deliberately. "We choose this moment," he said, "to challenge this generation and the next, to make sure this record is not long-lived. This is not triumphalism. It is a passing of responsibility. The record that has just been set is meant to be broken, and the breaking of it depends on what the people currently watching decide to do. The generation watching the Artemis II mission, particularly the generation young enough that the moon landing feels like something that happened to their grandparents, like ancient history, is the generation that will either go back or not. Hansen is Canadian, which matters specifically in this context. The Canadian Space Agency has been a partner in the ISS program for decades, and CSA astronauts have flown on NASA missions throughout that period. But deep space, historically, has been exclusively American and Soviet and Russian territory. The first human to leave Earth's gravitational neighborhood who was not either American or Russian. That is what Hansen is. He is the opening of a category. He spent time in the post-mission coverage talking about what this means for young Canadians in particular, but also for young people anywhere who have been watching human spaceflight as something that other countries do, something that has happened in other people's national mythology rather than theirs. The message is direct. The barriers that existed for the first 60 years of human spaceflight are being dismantled, one by one. And the question of who gets to go is being answered differently than it was in 1969. The Artemis II crew, as a unit, represents something specific about that change. A woman as mission specialist in deep space for the first time. A black astronaut in deep space for the first time. A non-American beyond Earth's orbit for the first time since 1991. A commander who raised 2 children alone after losing his wife and did not stop. These are not merely symbolic firsts. They are data points. They are evidence, accumulated in the bodies and records and returned words of 4 specific people. That the question of who can go is answerable differently than the answer that was given for the first half-century of human spaceflight. 2 days after the Artemis II crew splashed down, NASA held a press conference. Howard Hu, the Orion program manager, confirmed what engineers had expected. The heat shield came back with divots again, cracking, signs of uneven ablation. The new entry profile had helped significantly. The damage was less severe than Artemis I, but the pattern persisted. Hu was careful with his language. The shield had held. The crew was home. The investigation would determine what the data meant for future flights. The mission was a success. Simultaneously, and with a speed that several observers described as vertigo-inducing, the agency announced what comes next. 3 missions in roughly 2 years. A lander docking test. A crewed lunar landing. The beginning of a permanent base. All of it depending on hardware that, as of the morning of April 11th, had never carried a human being. Let's be precise about the timeline. Artemis III, currently targeted for mid-2027, 15 months away as you're listening, will not go to the moon. The original plan for Artemis III to land on the lunar surface was officially delayed in January 2026 and then restructured entirely in February. The new Artemis III will fly a crew of 4 to low Earth orbit, rendezvous with commercial lunar landers that have launched separately, and test the systems that future missions will depend on. This is the Apollo 9 parallel, the 1969 mission that tested the lunar module in Earth orbit before Apollo 11 landed on the moon. Nobody makes documentaries about Apollo 9. It was the mission that made everything else possible, by proving that the hardware worked together before it needed to work 250,000 miles from home. Artemis III is that mission. Not glamorous, not a distance record. Essential. The complications are significant. SpaceX's Starship human landing system needs to reach orbit and then be refueled by at least 14 separate tanker flights from a pre-positioned propellant depot that SpaceX also has to build and fill. Each tanker flight uses another Starship. The logistics of getting that much liquid methane and liquid oxygen into orbit, transferring it between vehicles that have never done an orbital fuel transfer with crew-rated systems, and then boosting the fully loaded lander to meet Orion, all within a tight launch window, is an engineering problem that would have seemed impossible 10 years ago. It may still be. Blue Origin's Blue Moon lander takes a different approach. smaller and more conventional in some ways, but it too has never flown with humans aboard. Both companies must complete uncrewed lunar landing demonstrations before NASA will allow crew inside. A March 2026 report from NASA's Office of the Inspector General noted that these demonstrations will not be fully representative of the crewed vehicles, meaning the first time these landers carry astronauts in their final configuration might be the actual mission. If neither company is ready in time, Artemis III is just another Orion flight in Earth orbit. Not useless, but not what the program needs it to be. The heat shield question is running in parallel to all of this. NASA's redesigned AVCOAT formulation, with better permeability, better gas venting during the temperature cycling that caused the Artemis I failures, is already being built into the Artemis III and IV capsules. The question the agency faces right now is whether the data from Artemis II's re-entry, combined with the Artemis I data, gives them enough confidence to certify the new design without another uncrewed test flight. Running a full uncrewed test mission costs roughly 2 years and $1 billion. Skipping it and flying crew on an uncertified redesign is exactly the kind of decision that the Columbia investigation identified as the failure mode in NASA's safety culture. This tension between the schedule pressure that comes from the race with China and the budget pressure that comes from an approximately $4 billion per launch vehicle on one side, and the engineering conservatism that has been beaten into the agency by 2 catastrophic losses and multiple near misses on the other, is the central drama of the Artemis program's next 2 years. It is not a drama that resolves clearly. It is a drama that gets managed imperfectly, mission by mission, by people who know the history and are trying not to repeat it. Assuming the lander tests succeed, Artemis IV follows in early 2028, the first crewed lunar landing in 56 years. 2 astronauts will descend to the Moon's south pole, a region that no human and very few robots have ever visited, a place completely unlike the flat equatorial plains where Apollo walked. The south polar region of the Moon is one of the strangest and most geologically significant places in the solar system, and it is worth spending time on what the 2 astronauts who descend there will actually be walking into. The Moon's axis of rotation is nearly perpendicular to the plane of its orbit around the Sun. Its axial tilt is only about 1.54 degrees, compared to Earth's 23.5 degrees. This means that near the lunar poles, the Sun never rises very high above the horizon. It skims along just above the surface, casting near horizontal light that illuminates some terrain in near-permanent sunlight, while leaving other terrain, anything inside a crater deeper than the Sun's grazing angle can reach, in permanent darkness. Those permanently shadowed regions have been in darkness not for years, not for centuries, but for billions of years, in some cases for essentially the entire age of the solar system. In that darkness, at temperatures as low as -250 degrees Celsius, just 23 degrees above absolute zero, nothing changes. No chemical reactions, no sublimation, no volatiles escaping. Whatever entered those craters has stayed there, frozen, since it arrived. What arrived there over billions of years of solar system history was water, delivered by comets and asteroids in a bombardment that shaped the entire inner solar system during its early history. Comets, which are largely water ice, have been striking the Moon throughout its history. Most of that water was immediately lost, boiled off by sunlight, broken up by ultraviolet radiation, scattered by solar wind. but some fraction of every impact, if the trajectory was right, ended up in a permanently shadowed crater near the poles. And once it got there, the cold kept it for billions of years. The Lunar Reconnaissance Orbiter, L-cross impact experiments, and neutron spectrometer data from multiple orbiters have built up a picture of the South Polar region that suggests significant water ice deposits in several of the permanently shadowed craters. Not uniform sheets of glacier ice, more likely patchy deposits mixed with regolith of varying concentration. But water, real water, billions of years old, preserved in cold so absolute it is nearly impossible to replicate in a laboratory. NASA has identified 9 candidate landing regions near the South Pole, each containing multiple specific sites. The final selection for Artemis IV depends on which lander flies and what its capabilities allow. Some sites offer better access to permanently shadowed regions where ice is most likely to be found. Others provide more consistent solar illumination for power generation. The South Pole's near horizontal sunlight means that ridge crests near the poles can be in near permanent sunlight, while the crater floors below them are in permanent shadow. The boundary between those two conditions is geographically complex and changes with the Moon's small axial wobble over time. The terrain near that boundary is some of the most scientifically valuable and operationally challenging real estate on the Moon. The 2 astronauts on Artemis IV who descend to the surface will spend approximately 1 week on the South Pole. They will conduct at least 2 spacewalks using the Axiom spacesuits tested on Artemis III. They will deploy a seismometer, the Lunar Environment Monitoring Station, designed to listen to the Moon's internal vibrations and map the structure of its crust and mantle in ways that Apollo seismometers, which were all on the near side, could not provide from the far side and poles. The Moon is seismically active in ways that still aren't fully understood, with moonquakes that can last for hours and that have different characteristics from terrestrial earthquakes in ways that tell you something about the structure of the lunar interior. They will drill. Subsurface sampling equipment will attempt to core below the surface at a permanently shadowed region, collecting material that has not been exposed to the space environment in billions of years. What those cores reveal about the specific chemistry and age of the polar deposits will answer questions about the early bombardment history of the inner solar system that no other mission can address. And then they will collect rocks, surface samples from a region of the Moon that has never been touched, material that formed in the South Polar crust under conditions different from the near-side equatorial sites where Apollo landed, processed by the same ancient impacts but at a different geometry, potentially preserving a different record of what the Moon's first billion years were like. They will leave a great deal behind. Everything they brought that isn't sample material, scientific instruments, or necessary for ascent. Boot prints in regolith that will last for millions of years, preserved by the same vacuum and lack of weather that preserves every impact crater. Evidence of a visit that, from the perspective of geological time, is instantaneous. 4 days in a 4 billion year record. And then they will climb back into the lander, ascend to meet Orion in orbit, and come home. The entire Artemis IV mission is expected to last about 30 days from launch to splashdown. For context, the longest Apollo surface stay was 3 days. Artemis IV will keep 2 people on the Moon for a week and 4 people in lunar space for a month. The increase in complexity over Apollo in terms of mission duration, crew time on the surface, and the range of activities planned is substantial even by the standards of the Apollo program, that put 12 people on the lunar surface across 6 landings. What comes after Artemis IV is where the mission ceases to be episodic and begins to be continuous. Artemis V, targeted for late 2028, is the beginning of the base. The first rover since Apollo 17. Pre-positioned infrastructure waiting for the crew to activate it. Construction, in the most literal sense. Components brought by robotic cargo deliveries that the crew will physically connect and test and integrate. The South Pole outpost that begins with 2 astronauts and a lander and is intended to grow, mission by mission, into something that people can live in for months at a time. NASA's target for continuous human habitation, a rotating crew, people living and working on the moon on a regular 6-month cycle, is 2032. 6 years. A permanent human outpost on another world in 6 years, starting from the day after Artemis II splashed down. The nuclear power system that will keep the base running during the 14-day lunar night, when solar panels produce nothing, is being developed at Idaho National Laboratory under a program called Kilopower, a reactor roughly the size of a desk, generating 10 kilowatts of electrical power, sufficient to operate life support and science equipment and communications through 2 weeks of darkness. Operational prototype tests in 2018 demonstrated the concept works. Flight qualifying the design for moon deployment is a different challenge, and that challenge is ongoing. The regolith processing system, extracting oxygen and hydrogen from lunar soil to produce rocket propellant and breathable air in situ, has been demonstrated in laboratory conditions. The actual South Polar regolith has never been processed by anything. Whether the deposits that remote sensing has identified will behave the way the laboratory models predict when a drill is actually put in them is something only the Artemis IV crew will be able to determine. Administrator Isaacman, in a statement shortly before the Artemis II launch, described the overall plan with a clarity that somewhat obscured its ambition. Keep flying, keep learning, keep iterating. This is the most important kind of institutional momentum in the history of any engineering program. The willingness to commit to a direction and absorb the failures along the way, rather than waiting until every question is answered before taking the next step. It is also, historically, the approach that produces the most dramatic learning events. Apollo 1 was the kind of failure that keep flying, keep learning produces. So was Challenger. So was Columbia. The people running Artemis know this. They are making a calculated bet that the cost of acceleration, the risk accepted by moving faster than complete certainty would allow, is lower than the cost of delay in a program that has limited political runway and a competitor that is not stopping. That bet may be right. The first 5 decades of crewed spaceflight were full of bets like it, and most of them were right. But all of the ones that were wrong were dramatically wrong, and the consequences were borne by specific people whose names are in the records. This is what it costs to go to the moon. It always has been. The 31 people whose deaths built the technical foundation that Artemis II flew on knew this in the ways they could know it before it happened. The Artemis II crew knew it in the way you know something when you have read the reports and made the decision anyway. And the people designing Artemis 3 and 4 and 5 know it in the way that people responsible for other people's lives always know it. As a weight that does not go away, that lives in the specific detail of every engineering decision, in every risk analysis, in every moment when the schedule pressure meets the engineering caution and a choice has to be made. Let's come all the way back. On April 1st, 2026, a rocket launched from Kennedy Space Center. It generated 8.8 million pounds of thrust, more than the Saturn V that sent Apollo to the moon. It carried 4 people on a trajectory that most humans alive today assumed they would never see in their lifetimes. Beyond Earth's orbit, to the moon, to the far side of the moon, further from Earth than any human had ever been. 10 days later, 4 people came home through fire. What they saw during those 10 days has been coming out slowly and will continue to come out for years. The far side geology that doesn't match the models. The eclipse that lasted 54 minutes and showed them a corona that rings an entire planetary body. The 6 impact flashes on a dark surface, evidence of a bombardment that never stops. The Earth set, their home disappearing behind a world that has no mercy, no air, no provision for anything alive. What they brought back is not just photographs and data, and bone marrow chips and saliva samples. They brought back a confirmation that we can do this, that the machines we built can carry people to the moon and bring them home, that the heat shield, imperfect, still being understood, still being improved, holds well enough for a crew to survive, that 4 human beings in a capsule the size of a large car can spend 10 days in the most hostile environment any human has entered in over half a century and come back capable of walking under their own. Power. This is not everything. The heat shield needs to be better. The radiation problem has no good solution yet. The landers have never flown with people. The South Pole has never been visited by anyone. The permanent base exists in planning documents and in the specific people who are working on it day by day. But the question of whether we can get back to the moon has been answered. We went. We came home. We named a crater for someone who asked one person she loved not to stop. And somewhere at the South Pole of the moon, in a region of permanent shadow so cold that water has been accumulating there since before life existed on Earth, ice is waiting. Ancient ice, delivered by comets billions of years ago, preserved in a cold so absolute that nothing has touched it since. Ice that has never been seen by human eyes, never sampled by human hands, sitting in a darkness that has existed since the solar system was young. Artemis IV is being built. The people who will walk on that ice are training right now. Some of them are in the NASA astronaut corps and know they're training for it. Some of them are in universities or test pilot programs or military flight schools and don't know yet that this is where they're going. Some of them are children who will watch the Artemis IV landing the way the generation before them watched Artemis II, or the generation before that watched Apollo 11, the way humans have always watched other humans go somewhere new, and felt something about it that's hard to name. Jeremy Hansen called on that generation specifically, not rhetorically, not as a closing flourish, but as a direct challenge. The record he had just helped set was meant to be broken. The breaking of it depended on what the people watching decided to do. This is the structure of exploration, in all its forms. You go as far as you can. You report back what you found. And then you tell the people listening, we got here, and here is what's further. You cannot see it from where we are. But it's there. Go. The Artemis II crew went as far as any human had gone in 53 years. They reported back what they found. A moon that is stranger than the models predicted. A far side that is not uniform grey but layered and complex, and old in ways that carry information about the solar system's first billion years. An eclipse that lasted 54 minutes and showed them a corona that rings a world. 6 flashes of micrometeorite impacts, that will inform the design of the habitats in which the next humans will sleep. A cold, dark, ancient South Pole, where ice is waiting. They reported back what the journey costs: 10 days of radiation accumulating in cells that will be monitored for the rest of their lives. A heart that spent 10 days practicing for a smaller world and had to be reminded on re-entry what a full-sized one feels like. A heat shield that held but is still not fully understood. A 6-minute blackout during which 4 people were alone with physics and history. And a decision that had been made months earlier that could not be unmade. They reported back what it looks like: a pale blue sphere shrinking to a golf ball, to a point to something below the threshold of visibility, disappearing behind a world that has no atmosphere and no mercy. And beyond it, the dark side that no human eye had seen from this close. And beneath them, the oldest terrain in the solar system. And above them a star whose outer atmosphere rings the entire rim of the moon in white fire. They came home. The records they set are meant to be broken. The data they collected is meant to be used. The ice at the South Pole is meant to be sampled. The lava tubes are meant to be explored. The granite anomaly that shouldn't be there is meant to be drilled. The permanently shadowed craters where cometary water has been accumulating for 4 billion years are meant to be walked into by people who will feel the specific quality of human curiosity at its most. Extreme, standing somewhere no one has ever stood, in conditions no one has ever survived, looking at something no one has ever seen. This is what the mission was for. Not the records and not the firsts, and not the photographs, though all of those matter. The mission was for the next one. There is a quality to what the Artemis II crew did that is easy to miss in the technical coverage, and the press conference language, and the careful institutional framing of a program managing both. Enormous ambition and enormous risk. They went to a place that no human had gone in 53 years. They did it on hardware that had never carried people to that distance before. They did it with a heat shield that had already failed once and been modified in response. They did it during solar maximum, in the full unshielded radiation environment of deep space, with no possibility of rescue if something went seriously wrong behind the moon. They did all of this, and they came back talking about the color of the regolith and the way shadows looked along the terminator, and a corona that rings the whole moon and 6 flashes on a dark surface. They came back curious, still interested, still looking outward. That is, in its way, the most extraordinary thing about the mission. Not the distance record or the engineering success or the historic firsts. The fact that 4 people went to the most extreme place humans have been in over half a century and came back wanting to go further. Victor Glover said the view from the far side was probably beyond what human beings had evolved to see. He said it not as a complaint. He said it as a description of something that had expanded him, that had taken the scale of what his mind could hold and stretched it past the boundary. Christina Koch watched Earth disappear behind the moon and said it made you understand what Earth provides. She didn't say it made her want to come home. She said it made her understand there is a difference. Jeremy Hansen challenged a generation to make the record not last long, not because the record itself matters, because the reaching matters, because the refusal to stay within the boundaries of what has already been done is what brought us here, and is what takes us further. Reed Wiseman named a crater for his wife. That is not nothing. In a mission full of data and science and technical achievement and historic firsts, a man named a feature on the boundary of the moon's known and unknown hemispheres for the woman who told him not to stop. The crater called Carol sits on that boundary, the near side and the far side, the visible and the hidden, the known and the not yet known. This is where we are. The ice at the South Pole is waiting. The next rocket is being built. The next crew is training. Sleep well. Good night.